Right now, 7 miles beneath your feet, something is moving in total darkness. The pressure would crush your skull in seconds. The cold would freeze your blood. Yet life thrives where it should not exist. We are descending to the deepest scar on Earth, a place so extreme it makes outer space look welcoming. If you enjoy exploring the unknown, hit that like button and subscribe. Take a breath. We are going down. In 1951, a British research vessel dropped a weighted wire into the western Pacific Ocean. The crew expected to measure another deep spot on the seafloor. The wire kept falling. It fell past the depth of Mount Everest if you flipped it upside down. It fell past every canyon, cave, and crevice ever measured on land. When the wire finally stopped, the crew checked their instruments 3 times. They had found a gash in the earth so deep it seemed impossible. The Mariana Trench stretches for over 1,500 miles near Guam. Scientists confirmed its maximum depth at nearly 36,000 feet below sea level. To picture this, imagine standing at the peak of Mount Everest. Now imagine another Mount Everest stacked on top of that one. You still would not reach the bottom of this trench from the ocean's edge above it. Here is what makes no sense. Earth's crust should not allow such extreme depths. Tectonic plates grind against each other, and one plate slides beneath another in a process called subduction. The Pacific Plate dives under the smaller Philippine Plate at this location. The angle and speed create a crack deeper than anywhere else in the known ocean. But the pressure at such depths should collapse the void. Rock should flow like putty under that much weight. Instead, the trench remains open, a wound in the planet that refuses to heal. Geologists struggled to explain it for decades. The descending plate pulls the seafloor down with immense force. Gravity assists this process, yet the trench walls do not crumble inward as models predicted. Recent research suggests the rocks deep underground behave differently than anyone anticipated. They stay rigid under extreme pressure instead of softening. This creates a stable pocket of space where none should exist. The discovery changed everything we thought we knew about ocean depth. Before 1951, scientists believed the ocean averaged around 12,000 feet deep. They assumed deeper areas might reach 20,000 feet at most. The Mariana Trench shattered those assumptions. It proved our maps were wrong and our understanding incomplete. What disturbed researchers more was the realization that we had barely explored our own planet. We had better maps of the moon's surface than of the seafloor beneath our oceans. The trench represented the ultimate blind spot, a place so remote and hostile that reaching it seemed nearly impossible with the technology available at the time. Early attempts to send equipment down resulted in crushed instruments and snapped cables. The pressure increases roughly 1 atmosphere every 33 feet of depth. At the bottom of the Mariana Trench, the pressure exceeds 16,000 pounds per square inch. That is more than 1,000 times the atmospheric pressure at sea level. Steel spheres designed for extreme depths crumpled like tin cans. Yet even in those first measurements, scientists detected something unexpected. The water down there was not still. Currents moved through the trench. Temperature readings showed variations. Chemical analysis revealed unusual compounds. These signs hinted at activity in a place that should be dead and frozen. Something was happening in that darkness. Something that would take decades more research to begin understanding. The Mariana Trench became an obsession for marine science, It represented the final frontier on Earth, more alien than any desert or mountaintop. Reaching the bottom would require engineering breakthroughs that seemed decades away. But before we could even think about touching the deepest point, we had to survive the journey down through layers of ocean that would test every limit of human endurance and technology. The descent begins in waters you might recognize, but it will not stay familiar for long. Your body starts betraying you almost immediately underwater. At just 50 feet below the waves, changes begin that most people never notice until something goes catastrophically wrong. The ocean does not give warnings, it simply applies physics to flesh and bone. The air in your lungs compresses. At 50 feet, the pressure has doubled compared to standing on a beach. The air you breathed at the top now occupies half the space inside your chest. Your lungs feel normal because water surrounds your body and creates equal pressure from all sides. But this balance is fragile and dangerous. Nitrogen begins dissolving into your bloodstream. Under normal pressure at the ocean's edge, nitrogen stays mostly in your lungs. When pressure increases, nitrogen molecules push into your blood and tissue like carbonation, forcing into soda. The deeper you go, the more nitrogen saturates your body. This process is invisible and painless. You feel nothing as your blood becomes a ticking time bomb. Recreational divers know 50 feet as the depth where mistakes become serious. Panic here and you might hold your breath while ascending. Those compressed gases in your lungs will expand as pressure decreases on the way up. Air can rupture through lung tissue into the bloodstream. Bubbles travel to your brain. You could have a stroke before you reach the open air above. The cold steals heat from your body 25 times faster than air does. Water conducts thermal energy away from your skin with brutal efficiency. Even in tropical oceans, prolonged time at 50 feet without protective gear leads to hypothermia. Your muscles stiffen, your thinking slows. You make poor decisions without realizing your judgment has deteriorated. Your ears feel the pressure first. The airspace in your middle ear wants to compress, but it cannot shrink because it is trapped behind your eardrum. The pressure differential pushes your eardrum inward. You feel pain, then intense pressure, then potential rupture if you do not equalize by forcing air through your eustachian tubes. Some people cannot equalize properly. For them, 50 feet might as well be 5,000. Their bodies simply cannot adapt. Scientists have confirmed that at 50 feet, you have entered a zone where your surface-dwelling biology works against you. Humans evolved to thrive at sea level with 14.7 pounds per square inch of atmospheric pressure. We have no natural defenses against the ocean's crushing force. Every foot deeper compounds the danger. Nitrogen narcosis begins affecting some divers around 70 feet, though sensitive individuals feel it earlier. The excess nitrogen acts like alcohol on your brain. You feel euphoric, confident, invincible. Divers have removed their air regulators underwater because they suddenly believed they could breathe like a fish. This is your brain malfunctioning under pressure. The narcosis will worsen as you descend. Commercial divers who work at 50 feet for extended periods face long-term damage. Their joints ache from repeated nitrogen exposure. Their bones develop tiny lesions where blood supply has been cut off by bubble formation. Their hearing degrades from pressure-related trauma. The ocean exacts a price for every minute spent in its grip. And this is just 50 feet. The creatures we are about to meet live in conditions that would kill an unprotected human in seconds. They have adapted to pressures that would pop your eyes from their sockets and collapse your ribcage like cardboard. The journey continues downward into water where sunlight still reaches, but where familiar ocean life begins transforming into something stranger. The first 600 feet of ocean seems normal until you pay attention. Fish swim past in schools. Kelp forests sway in the current. Dolphins patrol for prey. This is the sunlight zone, the only layer of ocean most people ever see. But even here, life adapts to challenges we barely understand. Sunlight penetrates this zone with enough intensity for plants to perform photosynthesis. Phytoplankton drift through the water column, forming the base of the entire ocean food chain. These microscopic organisms produce more than half the oxygen in Earth's atmosphere. Every second breath you take comes from these tiny life forms floating in sunlit water. Without them, terrestrial life would suffocate within years. The temperature drops as you descend through this zone. Near the top, water might reach 80 degrees Fahrenheit in tropical regions. At 600 feet, it has dropped to around 50 degrees. This gradient creates layers where different species thrive. Warm water fish stay near the top. Cold adapted species hover deeper. Cross those temperature boundaries and creatures become stressed, vulnerable, eventually dead. Sharks hunt in these waters with senses that seem supernatural. A great white shark can detect one drop of blood diluted in 25 million drops of seawater. Their ampullae of Lorenzini pick up electrical signals from muscle contractions of prey. They can sense your heartbeat from across a football field. These predators have ruled the sunlight zone for over 400 million years, longer than trees have existed on land. Sea turtles navigate these waters using Earth's magnetic field. Scientists confirmed they possess an internal compass calibrated to magnetic north. Hatchlings memorize the magnetic signature of their birth beach, then travel thousands of miles across open ocean. Decades later, they return to that exact beach to lay eggs. They detect variations in magnetic intensity that humans cannot measure without instruments. But the sunlight zone holds dangers beyond predators. Jellyfish drift through these waters trailing tentacles loaded with venom. The Portuguese man-of-war looks like a single organism, but is actually a colony of specialized polyps working together. Its tentacles extend over 100 feet. A single sting delivers toxins that cause welts, intense pain, and in rare cases, cardiac arrest. Even dead jellyfish washed up on beaches can sting for weeks. Coral reefs cluster in the sunlight zone, creating underwater cities that rival rainforests in biodiversity. A single reef might host over 4,000 species of fish, plus countless invertebrates, algae, and microorganisms. These reefs cover less than 1% of the ocean floor, yet support 25% of all marine life. They grow at rates of less than 1 inch per year. Some reefs took thousands of years to reach their current size. Scientists recently discovered that fish communicate with sound in the sunlight zone. They grunt, croak, and hum at frequencies we never noticed before. Underwater microphones became sensitive enough. Reefs produce a constant symphony of biological noise. This acoustic landscape helps larval fish find their way home after drifting in open water. Noise pollution from ships disrupts this communication, leaving young fish lost and vulnerable. The light penetrating this zone is not pure white. Water absorbs red wavelengths first. By 30 feet deep, red objects appear grey or black. Orange disappears next, then yellow. At 600 feet, only blue light remains. This creates a world where colors fade progressively, where blood appears green, where the spectrum narrows to shades of blue and black. Free divers push to depths of over 400 feet in this zone on a single breath. The current record exceeds 800 feet. These athletes train their bodies to withstand pressure that collapses their lungs to the size of oranges. They dive into oxygen debt so severe their heart rates drop to under 10 beats per minute. Then they must ascend before hypoxia shuts down their brain. One miscalculation means drowning in sight of sunlight streaming from above. But what waits deeper turns these risks into child's play. At 600 feet, the ocean enters permanent dusk. This is the twilight zone, where sunlight becomes so faint that most creatures rely on other senses to survive. Photosynthesis becomes impossible. Plants cannot grow here. Every organism must hunt, scavenge, or wait for food to drift down from the sunlit waters above. Over 90% of creatures in this zone have evolved bioluminescence. They produce their own light through chemical reactions in specialized organs called photophores. Bacteria living inside these photophores generate light when mixed with oxygen and a chemical called luciferin. The glow ranges from faint blue to bright green. This is not decoration. This is survival. The hatchetfish has a body shaped like an axe blade, thin and reflective. Photophores line its belly, emitting light that matches the faint sunlight filtering down from above. When predators look up, they see no silhouette, no shadow. The hatchetfish becomes invisible through counter-illumination. It adjusts the brightness of its glow to match changing light conditions. Too bright and it stands out. Too dim and its shadow gives it away. The dragonfish hunts using a headlight mounted below its eye. This photophore produces red light, a color almost no deep-sea creature can see. Most species lose the ability to detect red wavelengths because red light does not penetrate this deep naturally. The dragonfish evolved an advantage that amounts to infrared night vision. It illuminates prey that have no idea they are being watched. Lanternfish fill the twilight zone in numbers that stagger researchers. They might represent the most abundant vertebrate on Earth by sheer biomass. Billions upon billions of these small fish migrate vertically every night. At dusk, they rise toward the sunlight zone to feed on plankton. Before dawn, they descend back into the twilight zone. This journey covers 3,000 feet or more, twice daily for their entire lives. The reason relates to safety. Predators hunt more efficiently in bright water. By feeding at night and hiding deep during the day, lanternfish reduce their chances of being eaten. But this migration moves nutrients from the deep ocean to shallow waters and back again. It is one of the largest movements of biomass on the planet, and most humans have no idea it happens every single night. The viperfish waits in ambush with teeth so long, they cannot close their mouth completely. These fangs act like prison bars, trapping prey once bitten. The viperfish's jaw unhinges, allowing it to swallow fish larger than its own head. Photophores along its belly attract prey upward. Small fish see the glow and assume they are looking at the light zone above. They swim toward what they think is safety. The viperfish strikes from below. Scientists recently confirmed that some species use bioluminescence for communication. Certain squid flash patterns of light that might represent a language. They signal to potential mates, warn rivals, and coordinate hunting strategies. The ocean's twilight zone might host conversations we cannot decode, entire cultures of light-based communication happening in darkness we can barely penetrate. The stoplight loosejaw fish possesses one of the most bizarre adaptations in the twilight zone. It has no floor to its mouth, just hinged jaws connected by a stretchy skin. This allows the jaw to drop open incredibly wide, creating suction that pulls prey inward. Red photophores beneath its eyes produce light, giving it the dragonfish advantage. But unlike dragonfish, the loose jaw can open its mouth without warning prey. There is no closed jaw to avoid, no visible threat until the suction activates. Temperature continues dropping through the twilight zone. By 3,000 feet, water hovers around 40 degrees Fahrenheit. Pressure increases relentlessly. At 2,000 feet, pressure reaches nearly 1,000 pounds per square inch. A human transported instantly to this depth would be crushed before neurons could fire a pain signal to the brain. The Twilight Zone contains more fish biomass than all of humanity's current fishing catches combined. Yet we have barely begun exploring this layer. New species are discovered regularly. Some might hold medicinal compounds useful for cancer treatment. Others produce enzymes that work in extreme conditions, valuable for industrial processes. But the deeper we go, the stranger life becomes. Beyond 3,000 feet, even the faintest whisper of sunlight disappears forever. At 3,000 feet, you enter total darkness. No sunlight has ever reached this depth in the history of Earth. This is the Midnight Zone, stretching from 3,000 feet to 13,000 feet deep. Here, the concept of day and night becomes meaningless. Time itself loses the rhythm that governs life above. The water temperature stabilizes near freezing. In most parts of the ocean, the Midnight Zone hovers just above 32 degrees Fahrenheit. Only the salt content prevents the water from turning to ice. Pressure continues climbing toward 1 ton per square inch. At 4,000 feet, pressure would crush a car into a cube the size of a briefcase. Food becomes scarce in the Midnight Zone. No plants grow here. No phytoplankton drifts through these depths. Every scrap of nutrition must fall from above or be hunted from living creatures. Scientists call this rain of organic matter marine snow. Dead plankton, feces, molted shells, and decomposing organisms sink through the water column like an underwater blizzard. Most gets consumed before reaching the Midnight Zone. What arrives is picked clean by swarms of hungry scavengers. The anglerfish has become the iconic predator of this zone, though most people recognize only the female. She drifts motionless in the current, a bulbous body covered in dark, loose skin. A modified spine extends from her forehead, tipped with a bioluminescent lure. Bacteria in the lure produce a glowing light that attracts prey. Small fish investigate what they think might be food or another creature. The anglerfish strikes with jaws that open wider than her entire body. Male anglerfish live as parasites. They are 1/10 the size of females and have one purpose: reproduction. When a male finds a female in the vast darkness, he bites into her flesh. His mouth fuses permanently with her body. His organs degenerate until he becomes nothing more than a sperm-producing appendage. Multiple males can attach to a single female. She absorbs nutrients from her prey and shares them with the males through their fused circulatory systems. Scientists confirm this bizarre reproductive strategy solves a critical problem in the Midnight Zone. Mates are nearly impossible to find in total darkness across millions of cubic miles of water. Once a male locates a female, he never lets go. This guarantees fertilization when the female releases eggs. Evolution found a solution that seems horrific by our standards, yet it works perfectly for deep-sea survival. The gulper eel swims through these waters with a mouth larger than the rest of its body combined. Its jaw unhinges to form a massive trap lined with tiny teeth. The stomach expands like a balloon, allowing the eel to swallow prey larger than itself. A bioluminescent organ at the tip of its whip-like tail flashes rapidly, possibly attracting prey or communicating with other eels. When food is this scarce, you cannot afford to pass up any meal, no matter how large. Barrel fish possess transparent heads filled with fluid. You can see straight through their skulls to their barrel-shaped eyes inside. These eyes point upward, constantly scanning for the silhouettes of prey backlit by bioluminescence. The fish can detect the faintest glow from thousands of feet away. When scientists first discovered barrel-eye fish, they thought the specimens were damaged. Transparent heads seemed too strange to be real, but submersibles captured video of living barrelies confirming their anatomy. Pressure affects organisms differently in the midnight zone. Fish here lack swim bladders, gas-filled organs that help shallow water fish control buoyancy. Gas compresses under pressure, making swim bladders useless and dangerous in deep water. Instead, midnight zone fish use oils and fats that do not compress. They achieve neutral buoyancy through body composition rather than internal air pockets. The zone hosts swarms of krill and other crustaceans that feed on marine snow. These tiny creatures form the base of the deep-sea food chain. They consume falling organic matter and convert it into protein. Larger predators hunt the krill swarms. Those predators become prey for even larger hunters. But every link in this food chain operates under energy scarcity. Metabolism slows to conserve calories. Movement becomes calculated and deliberate. The midnight zone extends over 10,000 feet in vertical depth. That is twice the height of any mountain in the continental United States. We have explored less than 1% of this zone with direct observation. Cameras and sensors capture fragments of life, but vast areas remain completely unknown. What survives in those unmapped regions might rewrite our understanding of biological limits. And yet, we are barely halfway to the deepest point on Earth. Something massive is descending into the midnight zone above us. A sperm whale, 60 feet long and weighing 50 tons, drops through the darkness like a submarine with a heartbeat. This is the deepest diving mammal on Earth, routinely reaching depths over 6,000 feet. Some recorded dives exceeded 8,000 feet. At those depths, the whale endures pressures that should collapse its lungs and rupture its organs. The whale's ribcage compresses as pressure increases. By 1,000 feet, the lungs have collapsed completely. Air moves from the lungs into rigid windpipe passages where nitrogen cannot dissolve into the bloodstream. This prevents nitrogen narcosis and decompression sickness that would kill a human diver attempting the same descent. The whale basically disables its lungs during the dive, relying on oxygen stored in muscle tissue and blood. Myoglobin saturates the whale's muscle tissue at concentrations 10 times higher than in terrestrial mammals. This protein binds to oxygen molecules and releases them slowly during the dive. The whale's blood volume relative to body size is also massive compared to land animals. More blood means more oxygen storage. Together, these adaptations let a sperm whale hold its breath for 90 minutes while actively hunting in complete darkness. The whale navigates using echolocation clicks that reach 200 decibels. This is the loudest sound produced by any animal on Earth. Each click sends a sonar pulse through the water. Echoes bounce back from the seafloor, from swimming prey, from the bodies of other whales miles away. The whale's brain processes these echoes into a three-dimensional map, more detailed than anything human technology can create at depth. Scientists confirmed that sperm whales hunt giant squid in the midnight zone. Squid beaks have been found in whale stomachs, some from specimens over 40 feet long. These battles happen in total darkness under crushing pressure. The squid strikes with barbed tentacles. The whale responds with jaws lined with teeth that can snap a telephone pole. Suction cup scars covering the whale's head tell the story of countless encounters. The whale's body temperature remains near 98 degrees, despite swimming through water just above freezing. Blubber up to 14 inches thick insulates against the cold. Blood flow redirects away from the skin during deep dives, conserving heat in the body's core. The heart rate drops to as low as 3 beats per minute. With reduced circulation and collapsed lungs, the whale enters a state that resembles suspended animation. But physiology explains only part of the mystery. How does a warm-blooded mammal, producing metabolic heat, avoid dying from the bends during ascent? Humans ascending from just 200 feet must stop at intervals to let nitrogen escape slowly from their tissues. A sperm whale rockets from 8,000 feet to the ocean's edge in 30 minutes with no ill effects. Recent research suggests the answer lies in how the whale's body handles nitrogen. Collapsed lungs prevent nitrogen from entering the bloodstream under pressure. The small amount of nitrogen in the whale's tissues before the dive stays mostly dissolved during ascent, because the whale ascends slowly enough for gradual off-gassing. Additionally, specialized fats in the whale's body may absorb excess nitrogen, preventing bubble formation. The whale must eat nearly 1 ton of squid and fish daily to fuel its dives. Each dive burns enormous energy stores. The whale surfaces to breathe, sometimes resting for 15 minutes before diving again. During that surface interval, it exchanges 90% of the air in its lungs with each breath. Humans exchange only 15% during normal breathing. This rapid gas exchange prepares the whale for another plunge into the abyss. Calves learn to dive by following their mothers into progressively deeper water. Young whales can only dive a few hundred feet initially. Their bodies must develop the muscle, myoglobin, and blood volume needed for deeper dives. It takes years for a young sperm whale to reach adult diving capacity. Those that fail to develop properly cannot hunt effectively and starve. The whale's presence in the midnight zone demonstrates that no environment on Earth remains entirely isolated from the surface. These mammals bridge two worlds, breathing air at the top and hunting in depths that would kill most vertebrates instantly. They prove that evolution can overcome almost any obstacle given enough time. But the whale will not follow us deeper. Beyond 8,000 feet, even this perfectly adapted mammal cannot survive. The creatures below have abandoned all connection to the world of air and light. A shape emerges from the darkness ahead, tentacles spread like roots searching for prey. This is Architeuthis dux, the giant squid, one of the most elusive creatures on Earth. It can grow over 40 feet long from the tip of its mantle to the end of its longest tentacle. Eyes the size of dinner plates stare into the void, the largest eyes in the animal kingdom. Those eyes detect the faintest bioluminescence from miles away. The pupil is larger than a human fist. Light gathering capability exceeds that of any mammal by orders of magnitude. In an environment where a single photon might represent food or a mate, these massive eyes provide an overwhelming advantage. The squid sees things in the deep ocean that remain invisible to our instruments. But vision alone does not explain how giant squid hunt in total darkness. Scientists now believe these creatures use a form of biological radar. Thousands of touch-sensitive cells cover their tentacles and arms. When the squid extends its appendages, it creates a sensory net that detects pressure changes from moving prey. Water displacement from a fish swimming 20 feet away registers as clearly as sound in air. The squid strikes with explosive speed. Its two longest tentacles shoot forward faster than a human eye can track. Serrated sucker rings lined with sharp chitin dig into prey flesh. Barbs hook into muscle tissue, preventing escape. Once the tentacles secure the target, the shorter arms pull the prey toward a beak hidden between the tentacles. This beak, made of the same material as fingernails but much denser, can slice through steel cable. The beak cuts prey into pieces small enough to pass through the squid's brain. Yes! The esophagus runs through the center of the brain. If the squid swallows something too large, it causes brain damage. Evolution designed a system where the creature must precisely measure each bite or risk destroying its own nervous system. This seems like a fatal flaw, yet giant squid have thrived for millions of years. Scientists rarely see living giant squid in their natural habitat. Most knowledge comes from dead specimens that wash ashore or get caught in fishing nets. These animals live primarily between 1,000 and 3,000 feet deep, well beyond the range of most research submersibles. Cameras occasionally capture fleeting footage, but the squid usually flees before detailed observation becomes possible. In 2012, Japanese researchers finally recorded the first footage of a giant squid in its deep-sea environment. The animal approached a bait suspended from a research vessel. For 23 minutes, the squid investigated the bait, wrapped tentacles around it, and displayed hunting behavior. The footage revealed that giant squids actively swim through the water column, rather than drifting passively. They hunt with intention and intelligence. The squid's body contains pockets of ammonia solution that provide buoyancy. Ammonia is lighter than seawater, allowing the squid to float without expending energy. But ammonia is also toxic. The squid's flesh tastes bitter and unpleasant to most predators. This chemical defense protects against attacks from sharks and large fish. Sperm whales remain the only predators willing to eat giant squid, despite the ammonia content. Bioluminescent bacteria live in the squid's skin, providing camouflage similar to the hatchetfish. The squid can control these bacteria, dimming or brightening the glow. When hunting, the squid might glow faintly to attract prey. When hiding from predators, it goes completely dark. This level of control over external light production represents a sophisticated adaptation to life in the midnight zone. Recent studies confirm that giant squid communicate through color changes in their skin. Chromatophores, special cells containing pigments, expand or contract to create patterns. These patterns flash across the squid's body in waves. Other squid interpret these signals over distances of hundreds of feet. The messages might indicate territory, mating availability, or warnings about approaching threats. The giant squid's nervous system is remarkably complex. The brain contains as many neurons as a dog's brain. Individual nerves in the tentacles process information locally, allowing lightning-fast reactions without waiting for signals from the central brain. Each tentacle acts semi-independently, hunting and grasping prey while the main brain coordinates overall strategy. Despite their size and hunting prowess, giant squid face a fundamental energy problem. Food in the deep ocean is scarce. The squid must conserve calories while remaining ready to strike when prey appears. Its metabolism runs slowly compared to shallow water animals. This cold-blooded approach to survival keeps energy demands low, but it also means the squid cannot sustain prolonged activity. One long chase might burn days' worth of stored energy, but the creatures ahead make even the giant squid seem ordinary. The midnight zone sparkles with living light. Thousands of creatures produce bioluminescence, creating patterns that shift and flow like stars seen through turbulent air. This is not random. Every flash serves a purpose: attraction, communication, deception, or defense. The cookie cutter shark circles in darkness, its belly glowing bright blue-green. Photophores arranged in a band emit light that matches the faint bioluminescence of the zone. But the shark leaves one patch of skin dark on its underside. From below, the dark patch looks like a small fish silhouetted against the glowing background. Larger predators rise to investigate what they think is easy prey. The cookie cutter shark strikes, using specialized teeth to carve out a plug of flesh, then disappears into the darkness before the victim reacts. This hunting strategy has left scars on great white sharks, whales, and even nuclear submarines. The scars appear as perfect circles, evidence of an attack the victim never saw coming. Navy personnel initially thought the damage to submarines came from enemy weapons. Eventually, marine biologists identified the cookie cutter shark as the culprit. A creature the size of a house cat attacks submarines, using light as a lure. The flashlight fish carries bioluminescent bacteria in pouches beneath its eyes. The glow is so bright you could read a book by it in a dark room. The fish can rotate the light organs to face inward, shutting off the glow instantly. It uses this on-off mechanism to confuse predators. Flash, swim in one direction, go dark, change direction. Predators lose track of the fish's position in the darkness. Colonies of flashlight fish create coordinated light displays. Dozens of individuals flash in synchronized patterns that might serve as communication. Scientists observed these colonies blinking in sequence, like Christmas lights programmed to flash one after another. The purpose remains unclear, but the complexity suggests intelligence and social organization beyond what most fish species demonstrate. The bristlemouth fish outnumbers every other vertebrate in the ocean. Billions live in the midnight zone, perhaps trillions globally. They are small, barely 3 inches long, and covered in photophores arranged in rows along their bodies. Each species has a unique pattern of lights. These patterns help individuals identify their own species in total darkness. Mating depends on recognizing the right light signature. Scientists studying bristlemouths discovered they form the base of the deep-sea food chain. Nearly every larger predator in the midnight zone feeds on bristlemouths or on creatures that eat bristlemouths. Without these tiny glowing fish, the entire ecosystem would collapse, yet most people have never heard of them. They represent one of the most successful animals on Earth by population, thriving in an environment humans consider lifeless. The vampire squid uses bioluminescence as a weapon. When threatened, it expels a cloud of glowing mucus from its arm tips. The glow lasts for several minutes, forming a sparkling cloud in the water. Predators focus on the bright cloud while the vampire squid flees in the opposite direction. The creature can produce multiple clouds, creating a minefield of bioluminescent decoys. The vampire squid is not actually a squid, despite its name. It represents a separate order of cephalopods, a living fossil that has remained virtually unchanged for over 300 million years. Its bioluminescent defense evolved long before most modern predators existed. This ancient strategy still works perfectly against contemporary threats. Deep-sea dragonfish produce bioluminescence in multiple colors. Most creatures in the midnight zone can only see blue and green light. The dragonfish evolved the ability to produce and detect red light, giving it a private communication channel. When a dragonfish wants to signal another dragonfish without alerting prey or predators, it uses red bioluminescence. To every other creature in the area, the signal remains invisible. This represents one of the most sophisticated uses of bioluminescence in the ocean. The dragonfish essentially create encrypted communication millions of years before humans invented the concept. It can hunt illuminated by red light, coordinate with other dragonfish using red flashes, and remain undetected by species that only see blue and green wavelengths. The midnight zone produces more bioluminescence than all the stars visible in the night sky combined. If you could stand in the zone and see the complete spectrum, the display would overwhelm your senses. Creatures flash, pulse, glow, and sparkle in every direction. Some patterns repeat predictably, others appear random. Together they form a language of light written in biochemistry and evolution. But this abundance of life exists in conditions that test the limits of survival. The pressure continues, increasing with every foot deeper. Between 1,000 and 4,000 feet, you enter a layer of water that should not support life. This is the oxygen minimum zone, where dissolved oxygen drops to levels so low that most creatures suffocate. The water here contains less than 1 milliliter of oxygen per liter of seawater. Compare that to ocean shallows, where oxygen levels reach 8 milliliters per liter. Breathing here is like trying to survive in air at the top of Mount Everest. The zone forms due to biological processes above and physical processes below. Bacteria and other organisms consume oxygen as they decompose sinking organic matter. At the same time, this layer sits below the depth where waves and currents mix oxygenated water from the atmosphere into the ocean. Fresh oxygen does not reach this zone efficiently. The result is a horizontal layer stretching for hundreds of miles in some oceans where oxygen nearly vanishes. Animals trapped in the oxygen minimum zone enter a state of slow motion survival. Their metabolism decreases dramatically. Movement becomes rare and calculated. Growth slows to barely measurable rates. These creatures exist in a permanent state of near suffocation, their bodies operating at the minimum level required to stay alive. The jumbo squid thrives in this oxygen-starved layer during the day. It possesses an unusually efficient respiratory system that extracts oxygen from water other creatures would consider unbreathable. Gills larger in proportion to body size than other squid species pull every available oxygen molecule from the surrounding water. At night, the jumbo squid migrates upward to hunt in better oxygenated layers, then returns to the oxygen minimum zone at dawn. This migration provides protection from predators that cannot tolerate low oxygen. The jumbo squid essentially hides in an environment that kills most other large animals. It is a survival strategy based on metabolic efficiency rather than speed or size, but it comes with costs. The squid's growth rate and reproductive output remain lower than squid species living in well-oxygenated water. Scientists discovered that the oxygen minimum zone is expanding in many parts of the world ocean. Climate change is warming the upper ocean layers, reducing oxygen solubility in seawater. Warmer water holds less dissolved gas than cold water. Additionally, increased stratification prevents oxygen-rich surface water from mixing with deeper layers. The result is a gradual expansion of the oxygen minimum zone, both vertically and horizontally. Models predict that within 50 years, the oxygen minimum zone in some ocean regions could expand by hundreds of vertical feet. Species adapted to these conditions might thrive, but creatures dependent on higher oxygen levels will be forced into narrower bands of habitable water. The compression of vertical habitat zones could trigger ecosystem collapses in ways scientists are only beginning to predict. Certain species of octopus have adapted to the oxygen minimum zone by reducing their metabolic demands even further. They move slowly, hunting prey that is already weakened by low oxygen. Their bodies have evolved more efficient hemocyanin, the copper-based protein that transports oxygen in octopus blood. This hemocyanin binds oxygen more tightly than versions found in shallow water octopus species, ensuring maximum extraction from oxygen-poor water. Deep-sea shrimp swarms fill parts of the oxygen minimum zone in concentrations that seem impossible given the harsh conditions. These shrimp have evolved gills with enormous surface area relative to their body size. They also enter torpor states where metabolism drops close to zero, then wake periodically to feed on marine snow drifting through the water. This intermittent activity pattern allows survival on minimal oxygen. The expansion of the oxygen minimum zone represents one of the most serious threats to ocean ecosystems. Unlike warming water temperatures that change gradually and allow some adaptation time, oxygen loss can crash ecosystems rapidly. Fish and invertebrates cannot evolve low oxygen tolerance in a few generations. Mass die-offs become inevitable as the zone expands into previously well-oxygenated depths. Recent studies confirmed that bacteria thriving in the oxygen minimum zone produce nitrous oxide as a metabolic byproduct. Nitrous oxide is a greenhouse gas 300 times more potent than carbon dioxide over a 100-year period. The expanding oxygen minimum zone might create a feedback loop where climate change expands low oxygen zones, which then produce more greenhouse gases, which accelerates climate change further. The ocean is transforming in ways that could amplify global warming beyond current predictions, and we are still descending into even more extreme conditions ahead. At 13,000 feet, the pressure exceeds 6,000 pounds per square inch. Every square inch of your body would feel the weight of 3 cars stacked on top of each other. This is the depth where the midnight zone ends and the abyssal zone begins. Here, the ocean demonstrates forces that turn steel into crumpled metal. In 1963, the nuclear submarine USS Thresher imploded at approximately 2,300 feet during sea trials. The hull was rated for 1,300 feet maximum operating depth. When the submarine exceeded its crush depth, seawater pressure overwhelmed the steel hull in milliseconds. The submarine collapsed like a beer can stepped on by a boot. All 129 crew members died instantly. Their bodies were never recovered. The pressure was so intense that human remains were compressed into fragments too small to identify. Submersibles designed for the deepest ocean trenches must be built from materials that defy normal engineering principles. Titanium spheres with walls 7 inches thick provide the only reliable protection against abyssal pressure. The sphere shape distributes pressure evenly across the surface, preventing stress concentration that could trigger collapse. Windows are made of acrylic plastic cones mounted with the narrow end facing inward. This design allows pressure to compress the cone into its housing, creating a tighter seal as depth increases. The bathyscaphe Trieste reached the bottom of the Mariana Trench in 1960 using a spherical steel cabin, suspended beneath a float filled with gasoline. Gasoline was chosen because it is less compressible than water and lighter than seawater, providing buoyancy. The float was not pressurized, so external pressure could compress the gasoline without crushing the structure. Iron ballast pellets held the craft on the seafloor. When the crew released the ballast, the gasoline float pulled the sphere back to the surface. But even that engineering marvel came close to disaster. During descent, one of the observation windows cracked. The crew felt the pressure wave from the cracking glass inside the cabin. They had to decide immediately whether to abort the dive or continue deeper. They continued. The crack stabilized, and the window held. Had it failed completely, the cabin would have flooded in a fraction of a second. The pressure at that depth would have forced water through the opening with the velocity of a high-powered rifle bullet. Modern materials. Science has developed carbon fiber hulls that can withstand greater pressure at lower weight than steel. But these materials are expensive and difficult to manufacture. A single deep diving submersible costs tens of millions of dollars. Only a handful exist worldwide. This limits deep sea exploration to a tiny fraction of the ocean floor. We have sent more missions to the moon than to the deepest parts of our own planet. The pressure at 13,000 feet affects electronics in ways that surprise engineers. Circuit boards crack under pressure, changes, batteries leak, sealed containers implode. Every piece of equipment must be pressure tested before deployment. Even then, failures occur regularly. A camera housing rated for 10,000 feet might fail at 9,000 feet due to a microscopic flaw in the seal. The ocean is ruthlessly unforgiving of imperfection. Scientists recently discovered that abyssal pressure affects sound propagation in unexpected ways. Sound waves travel faster through pressurized water than through surface water, but they also lose energy more quickly to friction. The combination creates acoustic dead zones where sound simply disappears. This makes sonar mapping of the deepest trenches incredibly difficult. Large sections of the ocean floor remain unmapped because sound cannot penetrate the water column effectively. The human body would not explode at abyssal pressures as many people assume. Instead, you would implode. Air spaces in your lungs, sinuses and ears would collapse instantly. Your rib cage would crush inward. But your flesh, being mostly water and already at high pressure internally, would compress rather than burst. Death would occur in less than 1 second from multiple simultaneous trauma. there would be no pain. Your nervous system would not have time to process signals before catastrophic failure shut down brain function. Yet life exists at these pressures and thrives. Creatures we are about to meet have evolved bodies that function normally under forces that destroy human technology. They represent biological solutions to problems that still challenge our best engineers. Their existence proves that evolution can overcome any physical barrier given sufficient time. But how these creatures feed in an environment where every calorie is precious remains one of the deep ocean's greatest mysteries. A ribbon of darkness swims past, over 6 feet long, with most of that length being tail. This is the gulper eel, though calling it an eel barely captures its strangeness. The jaw unhinges to form a mouth larger than the entire rest of the body. When closed, the eel looks relatively normal. When open, it transforms into a living trap, a throat with fins attached. The gulper eel does not chase prey. It drifts through the abyssal zone with its mouth hanging open, waiting for something to swim inside. The jaw acts like a baleen whale's mouth, filtering food from the water column. Small crustaceans, fish, and squid that blunder into the open mouth cannot escape. Backward-pointing teeth line the throat, preventing anything from swimming out once it enters. Scientists initially thought the gulper eel fed exclusively on small prey due to its loose, bag-like stomach. Then researchers found a gulper eel with a fish twice its size inside its stomach. The stomach had stretched like a balloon to accommodate the massive meal. This revealed that the gulper eel is an opportunistic predator willing to swallow anything it can fit in its mouth. And its mouth can fit almost anything. The tail ends in a complex bioluminescent organ that pulses with light. The organ contains multiple photophores arranged in a pattern unique to gulper eels. Scientists believe this lure attracts prey toward the eel's mouth. Though observations of living specimens are too rare to confirm the hunting strategy definitively, the lure might also serve to attract mates in the vast darkness of the abyssal zone. Recent research using remotely operated vehicles captured footage of gulper eels inflating their massive mouths even larger by gulping seawater. The eels appeared to be displaying for potential mates or rivals. The inflated mouth might serve as a visual signal in an environment where size intimidation matters for establishing territory. Once inflated, the eel slowly deflates by releasing water through its gills, returning to normal proportions. The gulper eel's body contains almost no muscle mass. It is mostly a long digestive tract with the swimming apparatus attached. This extreme specialization for feeding means the eel cannot swim fast or fight effectively. It must ambush prey or wait for food to drift within reach. Chasing active prey would burn more energy than the meal provides. The eel is a patient hunter optimized for a world where food arrives unpredictably and infrequently. Specimens brought to the surface often die before researchers can study them properly. The rapid pressure change as the net rises causes gas spaces inside the eel to expand catastrophically. Some specimens arrive at the surface with their stomachs forced out through their mouths by expanding gas. Others simply fall apart from decompression trauma. Most knowledge about gulper eels comes from dead specimens, limiting our understanding of their behavior and ecology. The eel's eyes are tiny relative to its body size, much smaller than other deep-sea fish at similar depths. This suggests the gulper eel relies more on detecting water movement and chemical signals than on vision. Lateral line sensors running along its body pick up vibrations from swimming prey. Chemoreceptors in the mouth taste the water for dissolved organic compounds that indicate nearby food sources. Gulper eels might live for decades based on growth ring analysis of ear bones from preserved specimens. But reproduction remains a complete mystery. No one has ever found gulper eel eggs or larvae. No one knows where they spawn or how the young develop. The entire reproductive cycle of these creatures occurs somewhere in the abyssal zone, beyond the reach of current research technology. The eel's ability to unhinge its jaw represents one of several independent evolutions of this trait in deep-sea fish. Viperfish, gulper eels, and several species of deep-sea angler possess similar jaw mechanisms developed separately through convergent evolution. This suggests that extreme jaw flexibility provides such a significant advantage in the food-scarce abyssal zone that natural selection drove multiple lineages toward the same solution. But the gulper eel's adaptation comes with limitations. The jaw is fragile. A strong predator could damage the delicate hinge points and leave the eel unable to feed. The eel must avoid confrontation with larger creatures. It survives by being overlooked, by drifting like debris through water so dark that predators cannot see it, unless it reveals itself with bioluminescence. And the creatures sharing this zone have evolved even more extreme adaptations to survive where the ocean floor should finally begin. At 13,000 feet, most of the ocean floor spreads out in endless plains of mud and sediment. This is the abyssal zone, covering more than 50% of Earth's total surface area. It is the largest habitat on the planet, yet we know less about it than we know about the surface of Mars. The pressure here exceeds 6,000 pounds per square inch. The temperature hovers just above freezing. No sunlight has ever touched this seafloor. The mud consists of the accumulated remains of trillions of organisms that lived and died in the water column above. Their shells, bones, and body parts drifted downward over thousands of years, settling into layers hundreds of feet thick. Some areas of the abyssal floor have not been disturbed in millions of years. The only disturbance comes from occasional earthquakes and the rare passage of a deep-sea creature. Manganese nodules litter the seafloor like potatoes in a field. These black lumps grow slowly as minerals precipitate from seawater onto small fragments of shell or rock. They grow at rates of millimeters per million years. A nodule the size of a grapefruit might be 20 million years old. Mining companies want to harvest these nodules for their metal content, but doing so would destroy ecosystems that took millions of years to develop. Sea cucumbers crawl across the abyssal floor ingesting mud and extracting the tiny amount of organic material mixed with mineral sediment. These creatures are essential to the ecosystem. They process vast quantities of sediment, recycling nutrients and keeping organic matter available to bacteria and other decomposers. Without sea cucumbers, the abyssal floor would become a sterile desert of dead sediment. One species of sea cucumber was observed sitting stationary on the seafloor with its mouth open, collecting marine snow as it drifted down. The creature had positioned itself in a current that channeled falling organic matter directly into its mouth. This behavior represents a level of intelligence and spatial awareness that most people do not associate with sea cucumbers. It chose its location deliberately and remained there for the hours that cameras could observe it. Abyssal octopuses glide over the sediment, hunting for small crustaceans and worms. These octopuses have modified their hunting strategies for an environment where speed is useless. They move slowly to conserve energy. When they detect prey, they extend their arms gradually, surrounding the target before striking. The octopus's soft body and flexible arms allow it to probe into burrows and crevices where rigid-bodied predators cannot reach. One octopus species discovered in the abyssal zone guards its eggs for over 4 years. This represents the longest egg-brooding period of any animal on Earth. The female octopus attaches her eggs to a rock formation and remains with them, not feeding, until they hatch. She aerates the eggs with water currents from her siphon and protects them from predators. By the time the eggs hatch, the female has used all her energy reserves and dies shortly after. This level of parental investment seems extreme until you consider the energy cost of producing eggs in such a food-poor environment. Tripod fish hover above the seafloor on elongated fins that act as stilts. They face into the current with their pectoral fins extended like nets. Tiny crustaceans and other planktonic organisms flow past. The fish detects vibrations with lateral line sensors and snaps prey from the water without changing position. This sit and wait strategy minimizes energy expenditure while still allowing active feeding. Recent sonar mapping revealed underwater mountains called seamounts rising thousands of feet from the abyssal floor. These mountains disrupt deep ocean currents, causing upwelling that brings nutrient-rich water from the seafloor toward the surface. The result is oases of life in the abyssal desert. Corals grow on seamounts at depths where they should not exist. Fish aggregate around these structures in numbers far exceeding the surrounding plains. But seamounts also concentrate human impact. Fishing boats target seamounts because fish cluster there. Bottom trawling nets scrape across seamount slopes, destroying coral colonies that took thousands of years to grow. These ancient ecosystems disappear in minutes, replaced by barren rock. The damage is permanent on human timescales. The corals will not recover within our lifetimes or our children's lifetimes. The abyssal zone hosts extremophile bacteria that survive on chemical energy rather than sunlight-derived organic matter. These bacteria break down compounds leaching from rocks and sediments, obtaining energy from chemical reactions that would seem impossible to support life. They represent the base of food chains completely disconnected from photosynthesis. Life has found a way to exist without any dependency on the sun. But even this extreme environment is about to become stranger. A crack in the seafloor ahead glows red. Superheated water erupts from the Earth's crust at temperatures exceeding 700 degrees Fahrenheit. This is a hydrothermal vent, a wound in the planet where magma-heated seawater explodes back into the ocean. The water here should boil instantly, but pressure at this depth prevents the phase change. Liquid water can exceed normal boiling point temperatures when under extreme pressure. The vent water contains dissolved heavy metals and sulfur compounds that would kill most marine life instantly. Lead, zinc, copper, arsenic, and hydrogen sulfide spew from the vent in concentrations thousands of times higher than the surrounding seawater. The water is acidic, reaching pH levels that would dissolve human tissue on contact. This is a plume of liquid poison erupting continuously from the ocean floor. Yet life thrives here in densities comparable to coral reefs. Tube worms cluster around vent openings in colonies so thick they resemble underwater forests. These worms can grow over 6 feet long. They have no mouth and no digestive system. They survive through a symbiotic relationship with bacteria living inside their bodies. The bacteria use hydrogen sulfide from the vent to produce organic compounds through chemosynthesis. The worms absorb these compounds directly into their tissue. The tube worms extend red plumes from their tubes into the vent flow. These plumes contain hemoglobin that binds both oxygen and hydrogen sulfide simultaneously, a feat that will be lethal to most organisms. The worms transport both chemicals to the bacteria in their bodies. The bacteria require hydrogen sulfide for energy and oxygen to power their metabolism. The worms act as chemical delivery systems for their internal bacterial partners. Scientists discovered hydrothermal vents in 1977 during an exploration of the Galapagos Rift. The discovery revolutionized our understanding of life's requirements. Before that day, all known ecosystems depended on photosynthesis as the primary energy source. The vent communities proved that life could exist on chemical energy alone, completely independent from sunlight. This discovery suggested that similar ecosystems might exist on ice-covered moons in our solar system, where liquid water flows beneath frozen surfaces. White crabs swarm around the vents in numbers that stagger researchers. These crabs are blind, their eyes reduced to non-functional stubs. They navigate by chemoreception, following gradients of chemicals flowing from the vents. The crabs feed on bacteria growing on rock surfaces and scavenge dead organisms that drift into the vent area. They must carefully regulate their distance from the vent opening to avoid being boiled, while staying close enough to access the food-rich zone. The vents create temperature gradients measured in inches. Water 3 feet from the vent opening might be 200 degrees Fahrenheit. Water 2 feet away might be 100 degrees. Water 5 feet away returns to the ambient abyssal temperature of 36 degrees. Organisms must evolve heat tolerance while also surviving near-freezing conditions just beyond the vent influence. This dual adaptation challenge produces some of the most specialized creatures on Earth. Vent shrimp cluster so densely around some vents that they completely obscure the rock beneath. These shrimp have light-detecting organs on their backs rather than their heads. The organs cannot form images, but they can detect the faint infrared radiation from the superheated vent water. The shrimp use this heat detection to navigate closer to the vent than most creatures can tolerate, giving them access to prime feeding spots where bacteria growth is most intense. Giant clams anchor themselves in cracks near vent openings. Like the tube worms, these clams host chemosynthetic bacteria in their gills. The clams filter vent water through their gills, feeding the bacteria while filtering out heavy metals before the water contacts their vital organs. Some of these clams have been aged at over 250 years old. They might be the slowest growing animals on Earth, adding less than a millimeter of shell growth per year. Hydrothermal vents do not last forever. The geological processes that create them eventually shut down as tectonic activity shifts. When a vent dies, its ecosystem dies with it. The specialized creatures cannot survive in normal abyssal conditions. They must find new vents or perish. Scientists have documented dead vent fields littered with empty shells and abandoned tube worm structures. These ghost towns on the seafloor show how fragile even the hardiest ecosystems can be. But active vents keep forming as tectonic plates continue their endless grinding movement. New vent communities develop from larvae drifting in deep ocean currents. Somehow, these larvae find new vents across vast distances of barren seafloor. The mechanisms of this dispersal remain poorly understood, but life always finds these oases of chemical energy within years of their formation. The creatures we will meet next have taken specialization to even more bizarre extremes. A pale crab waves its claws through vent water in rhythmic motions. Dense white fur covers its arms and legs. But this is not fur. These are filaments densely packed with chemosynthetic bacteria. The crab is farming. It cultivates bacterial gardens on its own body and harvests them for food. This is the Yeti crab, discovered in 2005 on a hydrothermal vent near Easter Island. The crab deliberately positions itself where vent water mixes with cold seawater. This mixing zone provides optimal conditions for bacterial growth. Too close to the vent and heat kills the bacteria. Too far away and the bacteria lack hydrogen sulfide for energy. The crab dances back and forth across the temperature gradient, maximizing bacterial productivity on its limbs. Scientists observed Yeti crabs using their claws to scrape bacteria off their arms and into their mouths. They groom themselves constantly, redistributing bacteria and harvesting excess growth. This behavior represents a form of agriculture. The crab plants bacteria through proximity to chemical-rich water, tends the crop by maintaining optimal position, and harvests the yield when growth reaches sufficient density. Multiple Yeti crab species have been discovered since the first finding. One species lives on vents so deep that adult crabs must release their larvae into currents that carry them thousands of feet upward. The larvae drift in the water column, feeding on marine snow, until they mature enough to descend back to vent environments. This life cycle requires the larvae to survive in conditions completely different from their adult habitat, a remarkable adaptation challenge. Another Yeti crab species crowds around vents at densities exceeding 600 individuals per square yard. They pile on top of each other in writhing masses, all competing for position near the vent opening. The crabs on the bottom layer get crushed by the weight of those above. Dead crabs are immediately consumed by the living. This creates a brutal feeding hierarchy where position determines survival. Male Yeti crabs defend territories around the most productive bacterial growth zones. They fight with claws, attempting to rip bacterial filaments from rivals' arms. A crab with damaged bacterial gardens faces starvation until its filaments regrow. These territorial battles represent competition for agricultural land on a microscopic scale, fought with the same intensity as human wars over fertile soil. The bacteria on Yeti crab arms produce compounds that are toxic to most other organisms. This protects the crab from predators. Fish that attempt to eat Yeti crabs become sick or die from bacterial toxins. The crab essentially armors itself with poisonous bacteria, turning its food source into a defensive weapon. Yeti crabs have reduced eyes, though not completely blind like some vent creatures. They can detect light and shadow, but cannot form clear images. Their primary senses are chemical detection and touch. Chemoreceptors as their antennae analyze water flowing past, detecting gradients of hydrogen sulfide that guide them toward optimal farming locations. The reproductive cycle of Yeti crabs remains largely mysterious. Females carry fertilized eggs on their abdomens for extended periods, possibly years. The eggs must be brooded in water warm enough to promote development, but not so hot that they cook. Females presumably position themselves carefully during the brooding period, maintaining a delicate balance between competing thermal requirements. Recent genetic analysis revealed that yeti crabs are more closely related to hermit crabs than to other deep-sea crustaceans. Their ancestors likely inhabited shallow water before colonizing hydrothermal vents. The bacterial farming adaptation evolved after the crabs moved to deep water, not before. This suggests that the deep ocean drives innovation through extreme selection pressure, forcing rapid evolution of novel survival strategies. Some yeti crabs have been observed consuming vent shrimp in addition to their bacterial gardens. This supplemental predation provides protein and nutrients that bacteria cannot supply. The crabs are not strictly herbivores farming bacteria. They are omnivores using agriculture as their primary food source, while opportunistically hunting when chances arise. The discovery of yeti crabs changed scientific understanding of symbiosis complexity. These crabs maintain stable bacterial cultures on their bodies while living in an environment that should sterilize surfaces through heat and toxic chemistry. They represent living proof that cooperation between species can overcome almost any environmental challenge. But the creatures ahead demonstrate that even in the abyssal zone, stranger partnerships exist. An octopus drifts past with ear-like fins flapping slowly. The fins resemble the cartoon elephant Dumbo's ears, giving this creature its common name. The Dumbo octopus hovers in the water column at depths exceeding 13,000 feet, far below where most octopuses can survive. Its body is soft and gelatinous, adapted for an environment where rigid structure becomes a liability under crushing pressure. The fins provide propulsion and steering. Unlike shallow water octopuses that crawl along the bottom, Dumbo octopuses spend most of their lives floating above the seafloor. They pulse their fins like wings, gliding through the darkness with surprising grace. This swimming style conserves energy compared to jet propulsion used by many other octopus species. In a food-scarce environment, energy efficiency determines survival. Dumbo octopuses have lost the ability to produce ink. There is no point in creating a smokescreen in total darkness, where predators rely on sensors other than vision. Evolution stripped away this defense mechanism as unnecessary, redirecting resources toward more useful adaptations like enhanced chemoreception and pressure tolerance. The octopus's body contains almost no hard structures. Its beak is the only rigid part, and even that is softer than in shallow water species. Bones and shells are liabilities at extreme depth. Pressure compresses solid structures, creating stress that can cause catastrophic failure. A soft, flexible body distributes pressure evenly, preventing damage. Scientists have observed Dumbo octopuses pouncing on prey from above. They spread their web, the membrane connecting their arms, like a parachute, and descend onto small crustaceans crawling on the seafloor. The web traps prey underneath the octopus's body. Arms then manipulate the captured animal toward the beak. This hunting strategy requires precision timing and spatial awareness in complete darkness. Dumbo octopuses have relatively large eyes compared to body size, but their vision is limited. The eyes likely detect bioluminescence rather than forming detailed images. Many abyssal creatures produce light, making bioluminescence detection a valuable hunting tool. The octopus tracks glowing prey while remaining dark itself, hunting from stealth. Reproduction in Dumbo octopuses differs from their shallow water relatives. Females carry eggs at multiple developmental stages simultaneously. They can release mature eggs continuously rather than in a single spawning event. This strategy hedges against the unpredictability of food availability in the abyssal zone. If conditions improve, the female can increase egg production. If food becomes scarce, she can suspend egg development until resources improve. Males use a specialized arm to transfer sperm packets directly into the female's mantle cavity. The female stores these packets, sometimes for months, until conditions are favorable for egg production. This delayed fertilization allows mating and egg production to occur at different times, decoupling a reproduction from chance encounters in the vast darkness. Dumbo octopuses have been recorded at depth below 20,000 feet, making them among the deepest dwelling octopuses known to science. At those depths, pressure exceeds 9,000 pounds per square inch. The octopus's body compresses under this force, but its internal pressure matches external pressure, preventing damage. It is like a water balloon submerged in water. The pressure compresses the balloon slightly, but it does not burst because internal and external pressures equalize. Different Dumbo octopus species have been identified based on body proportions, fin shape, and web structure. Some have fins positioned near the front of their body. Others have fins closer to the rear. These variations affect swimming efficiency and maneuverability. Species with forward fins can accelerate quickly. Species with rear fins have better turning ability. Evolution has experimented with multiple body plans, and all seem to work effectively in the abyssal environment. The octopus's mantle, the main body cavity, pulsates rhythmically even when the creature is stationary. This pumps water through the gills, ensuring continuous oxygen extraction from the already oxygen-poor water. Respiratory efficiency is critical at depth, where dissolved oxygen levels are minimal. The octopus cannot afford to let oxygenated water pass through its gills without extracting every available molecule. Dumbo octopuses face predation from deep-diving sharks and large fish, though encounters are rare. Their best defense is transparency. The gelatinous body allows some light to pass through, making the octopus less visible in the dim bioluminescence of the abyssal zone. Predators looking for solid silhouettes might overlook the nearly transparent octopus drifting nearby. But even this remarkable creature cannot venture deeper into zones where pressure reaches truly catastrophic levels. We have descended past 20,000 feet. The pressure now exceeds 8 tons per square inch. To visualize this force, imagine an African elephant standing on your thumb. Now imagine 49 more elephants stacked on top of the first one. That is the pressure at 20,000 feet depth. And we are still 5,000 feet away from the deepest trenches. This depth, materials behave in ways that defy surface world expectations. Foam coffee cups sent down in research equipment return the size of shot glasses, compressed by pressure that squeezes out all air pockets. The foam's cellular structure collapses completely. Wood becomes waterlogged and heavy, sinking rather than floating. Air trapped inside batteries compresses so much that the battery casings implode, spilling toxic chemicals into the water. The speed of sound through seawater increases with pressure. At 20,000 feet, sound waves travel about 5% faster than at the ocean's surface. This affects sonar systems and makes acoustic positioning more complex. Engineers must recalibrate instruments for each depth zone to maintain accuracy. Small errors in speed of sound calculations translate to position errors of hundreds of feet when mapping the seafloor. Water itself becomes slightly more viscous at extreme pressure. The pressure forces water molecules closer, together increasing resistance to flow. This has negligible effect on large-scale currents, but impacts small organisms. Tiny creatures swimming through pressurized water experience higher drag than the same creature swimming near the surface. This is another reason why deep-sea fish move slowly and deliberately. The freezing point of seawater increases under pressure. At 20,000 feet, seawater can remain liquid at temperatures below 28 degrees Fahrenheit. This supercooled water should freeze, but it remains fluid because pressure inhibits ice crystal formation. Disturb this water and it might flash freeze instantly, a phenomenon called supercooling. Though this is rare in the ocean, it demonstrates how pressure alters basic physical properties. Human technology reaches its limits at these depths. Most research submarines cannot dive below 20,000 feet. Those that can cost astronomical sums and require years of development. The pressure crushes sophisticated electronics. Seals fail. Hydraulic systems leak. Every component must be over-engineered to survive forces that no terrestrial environment can replicate. The bathyscaphe Trieste survived its dive to the Challenger Deep partly through luck. Modern analysis of the original design reveals several points of potential failure that somehow held during the descent. If the dive were attempted again with the same design, engineers estimate a significant probability of catastrophic failure. The crew of Trieste ventured into conditions that pushed 1950s technology far beyond its safety margins. Challenger Deep expedition filmmaker James Cameron described the pressure at maximum depth as feeling oppressive even inside the protective sphere. He said the submersible hull groaned and creaked continuously. Every sound made him wonder if that was the beginning of structural failure. The psychological pressure of knowing that death would come instantly if the hull breached made the experience more terrifying than any fiction film he had ever directed. Remotely operated vehicles equipped with standard cameras return footage from these depths that looks muddy and distorted. Pressure compresses the water-filled camera housing slightly, changing the lens spacing and ruining focus. Special cameras with pressure-compensating housings are required. These cameras cost tens of thousands of dollars each and still frequently fail. Scientists joke that deep-sea research equipment has two states, working and broken, with most time spent in the broken state. The few creatures surviving at this depth have abandoned almost every feature we associate with fish. No swim bladders, no gas-filled spaces anywhere in their bodies, minimal bone structure. They are built like soft machines, optimized for an environment where any internal air pocket becomes a crush hazard. Their bodies are approximately 90% water, matching the external pressure naturally. Some fish at this depth lack scales entirely. Scales add weight and rigidity, both disadvantages in deep water. Scaleless skin reduces energy costs for swimming and eliminates the need to grow and maintain protective plates that serve no purpose in an environment lacking high-speed predators. Evolution strips away everything except absolute necessities. Recent studies revealed that proteins in deep-sea fish have unique shapes, stabilized by pressure. These proteins denature and become non-functional if brought to surface pressure. The fish literally cannot survive at shallow depth because their biochemistry requires extreme pressure to work correctly. They are locked into their deep environment as surely as surface fish would be crushed diving down. The pressure continues increasing beyond 20,000 feet into zones where only trenches penetrate. These deepest scars in the earth represent the final frontier of ocean exploration. The creatures inhabiting trenches have evolved in isolation from the rest of the ocean, producing animals found nowhere else on Earth. And they feed on the most unexpected resources that drift down from above. A whale carcass rests on the seafloor at 18,000 feet. The body has been here for 3 years since it sank from the surface. Most of the soft tissue is gone, consumed by sharks and hagfish during the descent and by amphipods and crabs after it settled on the bottom. But the skeleton remains, and it has attracted a unique community of scavengers. Dozens of small worms cluster on the whale bones. These are zombie worms, scientifically named Osedax. They have no mouth, no stomach, no digestive system. They survive by penetrating into whale bones with root-like structures and secreting acid that dissolves the bone matrix. The worms absorb lipids stored inside the bone tissue. A single skeleton can support zombie worm colonies for decades, forming an oasis of life in the barren abyssal plain. The worms produce acid strong enough to dissolve calcium phosphate, the mineral making up bone structure. This ability is rare in nature. Most organisms cannot generate acids concentrated enough to break down bone. But zombie worms have bacteria living inside their tissues that produce the acid as a metabolic byproduct. Once again, symbiosis between animal and bacteria enables survival in an impossible environment. Female zombie worms grow up to 3 inches long, with red plumes extending from the bone surface to absorb oxygen from the surrounding water. Males are microscopic, less than 1 millimeter long. They live inside the female's body as parasites, existing only to fertilize her eggs. A single female can host dozens of males, all living as permanent internal residents. Scientists discovered zombie worms in 2004 on a whale skeleton in Monterey Bay at about 1,000 feet depth. Since then, they have been found on whale bones down to nearly 13,000 feet. The worms are specialists, found only on whale skeletons and occasionally on large fish bones. They represent an entire ecosystem dependent on the rare occurrence of large carcasses sinking to the deep sea floor. A single grey whale carcass provides enough nutrition to support a complex community of specialized organisms for up to 100 years. The first stage after sinking is dominated by mobile scavengers that consume soft tissue. The second stage belongs to enrichment opportunists that feed on organic material enriched into the sediment around the carcass. The final stage is the sulfophilic stage, where bacteria break down lipids in the bones, producing hydrogen sulfide similar to hydrothermal vents. Zombie worms dominate this final stage. Researchers calculated that whale falls, as these carcasses are called, occur frequently enough to create a network of deep-sea oases spanning the ocean floor. A large whale dies and sinks somewhere in the world ocean roughly every 8 miles on average. This creates stepping, stones of nutrition in the abyssal desert. Species can migrate from one whale fall to the next, maintaining genetic diversity across populations separated by vast distances. But commercial whaling in the 19th and 20th centuries dramatically reduced whale populations. Fewer whales means fewer whale falls. This has potentially impacted deep-sea ecosystems in ways scientists are only beginning to understand. Species dependent on whale falls might have declining populations or increased extinction risk. We have changed the deep ocean without ever visiting it, simply by killing whales at the surface. Zombie worms have relatives that colonize wood sunk in deep water. These wood-boring relatives produce different acids optimized for breaking down cellulose and lignin, rather than bone minerals. Trees that wash into the ocean from rivers occasionally sink to the deep sea floor, providing another rare food source. The worms have diversified to exploit both wood and bone, demonstrating impressive metabolic flexibility. Recent expeditions have sunk whale bones deliberately to study colonization rates. Within months, zombie worm larvae settle on the bones and begin penetration. The larvae drift in deep ocean currents, somehow detecting the chemical signature of sinking bones across miles of water. Once settled, the larvae metamorphose into their root-like adult form and never move again. Their entire adult life is spent anchored to a single spot, acid mining nutrition from ancient bone. The existence of zombie worms raises questions about past ocean ecosystems. Before whales evolved around 50 million years ago, what fed the ancestors of Osedax? Some scientists speculate that these worms originally fed on marine reptile bones when plesiosaurs and mosasaurs dominated the oceans. When those reptiles went extinct, the worms adapted to whale bones. This suggests the worms are at least 65 million years old, possibly older, making them one of the most ancient, specialized deep-sea lineages. We have now passed through most of the abyssal zone, but the ocean floor continues dropping into trenches that represent Earth's deepest scars. The Hadal Zone begins below 20,000 feet, named after Hades, the Greek underworld. Conditions there exceed what we have experienced so far. The creatures ahead exist at the absolute limits of where life can survive on our planet. At 20,000 feet, the seafloor drops away into darkness that seems darker than what we have already passed through. This is the Hadal Zone, the deepest 2% of the ocean found only in trenches where tectonic plates collide and one dives beneath the other. Only 27 places on Earth reach these depths. They are scattered across the Pacific Ocean like wounds that refuse to heal. The Hadal Zone begins where the abyssal plains end, and the trench walls plunge downward at angles approaching vertical. These are not gentle slopes. They are cliffs dropping thousands of feet into chasms that make the Grand Canyon look shallow. The Mariana Trench alone descends more than 7 miles below the waves. Mount Everest placed at the bottom would disappear with over a mile of water above its peak. Pressure in the Hadal Zone starts at 8 tons per square inch and climbs toward 8.5 tons as you descend deeper. This is the realm of extreme survivors, organisms that have adapted to conditions that destroy almost everything else. Life here operates under rules that seem to violate what we know about biology. Scientists once believed nothing could survive below 20,000 feet. They assumed pressure would crush all cells, denature all proteins, and prevent any metabolic processes from functioning. Early expeditions to Hadal depths found only barren mud. Researchers concluded the deepest trenches were dead zones, lifeless except for bacteria. They were wrong. In the 1950s, Danish research vessel Galathea collected amphipods, small, shrimp-like crustaceans, from depths exceeding 30,000 feet. The specimens proved that complex animals could survive in the Hadal Zone. But they also raised questions. What did these creatures eat? How did they withstand the pressure? Why weren't they crushed into paste? The amphipods brought up from Hadal, depths died within hours of reaching the surface. Their bodies fell apart as internal pressure that balanced external pressure at depth now had nothing to push against. Cells ruptured, proteins unfolded. The creatures literally dissolved as they died. This made studying them incredibly difficult. Scientists had to work fast, preserving specimens in chemicals before decomposition destroyed all anatomical details. Temperature in the Hadal zone varies more than in the abyssal zone above. Seawater near the trench walls can be slightly warmer than water in the open abyss due to geothermal heat leaking through the seafloor. This creates microclimates where temperature gradients of several degrees exist across just hundreds of feet. Some Hadal species cluster in these warmer zones. Others prefer the coldest water at the very bottom of the trench. Currents flow through Hadal trenches in patterns that scientists are only beginning to map. These currents carry organic material from the abyssal plains above down into the trenches. The currents also transport larvae and create connections between isolated trench populations. Without these currents, each trench would be completely isolated, and genetic diversity would collapse. The trench walls support unique ecosystems. Bacteria grow on rock faces, metabolizing chemicals leaching from the stone itself. These bacterial mats provide food for amphipods and other small crustaceans. Larger predators hunt the crustaceans. A complete food chain exists clinging to vertical cliffs in crushing darkness. Recent sonar mapping revealed that many trenches have complex topography. They are not simple V-shaped cuts. Instead, they contain underwater plateaus, isolated basins, and secondary depressions deeper than the main trench floor. Each of these features might host distinct communities of organisms. A trench 30 miles long could contain dozens of isolated microhabitats, each with its own endemic species. The Hadal zone represents the least explored major habitat on Earth. We have sent only a handful of crewed missions to these depths, and slightly more robotic vehicles. Most of the Hadal seafloor has never been seen by human eyes or cameras. New species are discovered on almost every expedition. Some trenches have never been explored at all. The creatures living here have abandoned characteristics we consider essential to animal life. They move slowly, grow slowly, reproduce slowly. Everything happens in slow motion because energy is so scarce that rapid activity means death. Yet they persist in conditions that annihilate our best technology. The fish ahead demonstrate just how strange Hadal adaptations can become. A fish drifts past that barely looks like a fish at all. Its body is translucent, almost gelatinous, with visible organs floating inside like parts suspended in clear jelly. This is a Hadal snailfish, holding the record for the deepest fish ever observed. Specimens have been recorded at depths exceeding 27,000 feet. Well into the Hadal zone where pressure approaches 8.5 tons per square inch. The snailfish has no scales. Its skin is smooth and loose, appearing too large for the body underneath. This loose skin distributes pressure evenly across the body surface. There are no hard edges or rigid structures where stress might concentrate. The skull is partially cartilaginous and incomplete. Gaps in the skull bones allow brain tissue to compress slightly under pressure without damage. Scientists studying Hadal snailfish discovered that the fish's bones contain a special organic compound that prevents minerals from crystallizing normally. This keeps bones slightly flexible rather than rigid. Flexible bones bend under pressure instead of shattering. The skeleton provides structural support while remaining adaptable to extreme force. The fish's muscle tissue has an unusual texture, softer than typical fish muscle. Analysis revealed high concentrations of a chemical called trimethylamine oxide, abbreviated as TMAO. This compound counteracts the pressure-induced changes that would normally denature proteins and disrupt cell membranes. TMAO stabilizes proteins, allowing them to function at depths where normal proteins would unfold and stop working. Hadal snailfish produce more TMAO than any other fish species measured. Concentrations increase with habitat depth. Fish living at 27,000 feet have TMAO levels nearly 20% higher than fish at 20,000 feet. This correlation suggests TMAO concentration directly limits how deep a fish can survive. Eventually, at some depth, there is a limit to how much TMAO can be produced. That depth might represent the absolute maximum where fish life can exist. The snailfish's digestive system occupies most of its body cavity. A large stomach allows the fish to consume prey items almost as large as itself. In an environment where meals are rare, the ability to eat opportunistically matters more than eating efficiently. The snailfish cannot afford to be picky. Anything small enough to swallow becomes food. Teeth line the snailfish's jaws in multiple rows. These teeth point backward, preventing prey from escaping once caught. The fish feeds primarily on amphipods and other small crustaceans that swarm in hadal trenches. The snailfish hunts by ambush, remaining motionless until prey swims within striking range. A sudden lunge and gulp capture the prey before it can react. Hadal snailfish have relatively large eyes compared to some deep-sea fish, but their vision is poor. The eyes detect movement and light changes rather than forming detailed images. This is sufficient for hunting in an environment where bioluminescence from prey provides the only light source. The fish tracks glowing targets and strikes when they come close enough. Reproduction in hadal snailfish remains poorly understood. No one has observed mating or found eggs in their natural habitat. Females captured during expeditions often contain developing eggs, suggesting they are live bearers or deposit eggs on the seafloor. The young must develop under the same extreme pressures as adults, implying they are born with full pressure adaptation already in place. Different trench systems host different snailfish species. The Mariana Trench snailfish differs genetically from species found in the Japan Trench or the Kermadec Trench. These trenches are separated by thousands of miles of abyssal plain that hadal species cannot cross. Each trench acts as an island of deep water surrounded by shallow abyss. Species evolve in isolation, producing unique adaptations in each location. Some hadal snailfish have been recorded swimming in small groups. This social behavior is unusual for deep-sea fish, which typically live solitary lives. The grouping might be related to mating or cooperative feeding. Alternatively, the fish might simply cluster around food sources like amphipod swarms. Without long-term observation, scientists cannot determine if the grouping is intentional social behavior or coincidental aggregation. The snailfish's heart beats slowly, around 10 beats per minute at rest. This slow metabolism conserves energy in an environment where food arrives unpredictably. the fish can survive weeks without eating by lowering its metabolic rate even further. This state resembles hibernation in mammals, though the fish remains alert enough to strike at prey if an opportunity arises. Hadal snailfish demonstrate that vertebrate life can exist at depths we once thought impossible. But even these extreme specialists have limits. Below approximately 27,000 feet, no fish have been found. Whether this represents a true physical barrier or simply the limits of current exploration remains unknown. But the creatures that do survive below that depth have taken adaptation to even more extreme levels. The amphipods ahead rival small dogs in size and demonstrate armor-plated defenses against pressures that would flatten steel. Something large scuttles across the trench floor ahead. This is a supergiant amphipod, measuring over 12 inches long. For comparison, amphipods near the ocean's edge typically measure half an inch. This creature is 20 times larger than its shallow water cousins. It moves through water at depths exceeding 30,000 feet, hunting in darkness under pressures that exceed 8 tons per square inch. The amphipod's exoskeleton is thick and reinforced, providing armor against predators and structural support against pressure. But unlike shallow water crustacean shells that are rigid, this exoskeleton has some flexibility. It can compress slightly under pressure without cracking. The joints between segments allow for articulated movement while maintaining pressure integrity. These giants are scavengers, feeding primarily on organic material that drifts down from above. They swarm over any food source that reaches the trench floor. When researchers deployed bait canisters in Hadal trenches, supergiant amphipods arrived within hours. They stripped fish carcasses to bone in a matter of days. Cameras captured dozens of amphipods fighting over access to the bait, climbing over each other in a frenzy of feeding activity. The amphipod's mandibles are powerful enough to crush fish bones and tear through tough tissue. These jaws operate with mechanical advantage, generating bite forces disproportionate to the creature's size. The mandibles also possess serrated edges that act like saws, allowing the amphipod to cut through materials that would resist simple crushing. Supergiant amphipods exhibit a phenomenon called deep-sea gigantism. Many groups of organisms grow larger in deep water than their shallow relatives. Scientists have proposed several explanations. Larger body size increases efficiency of energy storage and use. Larger bodies also maintain temperature better in cold water. Additionally, reduced predation pressure in the deep sea might allow organisms to grow larger without the size becoming a liability. But size comes with costs. Larger bodies require more food to maintain. In the food-scarce Hadal zone, this creates a paradox. Amphipods grow large because it provides advantages, but being large increases energy demands in an environment where energy is limited. The amphipods solve this by having extremely slow metabolisms. They can survive months without food, living off stored energy while waiting for the next carcass to sink within reach. The amphipod's sensory system is highly developed. Antennae covered in chemoreceptors detect dissolved, organic compounds from miles away. When something dies in the water column above and begins sinking, amphipods detect the chemical trail long before the carcass reaches bottom. They track the scent like bloodhounds, converging from across the trench floor. Recent studies using baited cameras revealed that supergiant amphipods can swim into the water column, ascending hundreds of feet above the trench floor. This suggests they actively hunt for sinking food rather than waiting passively for it to arrive. The ability to swim vertically through the water column requires significant energy expenditure, but increases the chances of intercepting food before competing scavengers claim it. Some supergiant amphipods have been found with smaller amphipods in their stomachs. This cannibalism occurs when food is scarce and population density is high. The largest individuals prey on smaller ones, turning competition into calories. This behavior is rare but documented, showing that Hadal scavengers will eat almost anything organic when faced with starvation. The amphipod's eyes are small and probably non-functional in most species. Vision is useless in total darkness where no light exists naturally, and bioluminescence is rare among Hadal organisms. Evolution has reduced eyes to vestigial structures, redirecting resources toward more useful senses like chemoreception and mechanoreception. Reproduction in supergiant amphipods follows a strategy common in deep-sea crustaceans. Females carry fertilized eggs in a brood pouch until they hatch. The developing embryos are protected from the external environment and receive some nutrition from the mother. This increases survival rates compared to broadcasting eggs into open water where they face harsh conditions immediately. Population density of supergiant amphipods varies dramatically depending on food availability. Areas near the central axis of trenches, where organic material accumulates, host dense populations. Areas on trench, slopes or outer edges might have sparse populations. An expedition might encounter hundreds of amphipods at one location, and none just a few miles away. Scientists have collected supergiant amphipods from multiple trenches across the Pacific. Each trench population shows genetic differences, indicating limited gene flow between trenches. Some populations have been isolated for millions of years, evolving unique characteristics. This makes each Hadal trench not just a geographic feature, but an evolutionary laboratory where species develop in isolation. The amphipods face an uncertain future. Climate change is altering ocean chemistry even at Hadal depths. Additionally, proposed deep-sea mining operations could destroy trench ecosystems before we understand them. These creatures survived millions of years of geological and climate changes. Now they face human impacts reaching even the deepest parts of the ocean. But the trench environment itself presents dangers that dwarf any human activity. The walls ahead reveal instability on a geological scale. The Mariana Trench walls drop away at angles exceeding 70 degrees in some sections. This is nearly vertical, a cliff face descending thousands of feet into darkness below. The walls are not smooth. They are fractured and broken, scarred by landslides and earthquakes. Massive blocks of rock, bigger than skyscrapers, have carved off the walls and tumbled to the trench floor below. Geologists studying trench formation initially expected gradual slopes created by sediment accumulation. They found the opposite. Trenches have steep walls because the subducting tectonic plate pulls the seafloor down at a sharp angle. The overlying plate resists, creating a hinge line where the seafloor bends dramatically. This creates structural stress that fractures rock and causes periodic collapses. Submarine landslides in trenches can move billions of tons of sediment and rock in minutes. These underwater avalanches generate enough force to snap undersea communication cables. In 1929, an earthquake off Newfoundland triggered a landslide that cut telegraph cables at depths exceeding 12,000 feet. The cables broke sequentially as the landslide passed, allowing scientists to calculate the slide's speed at over 50 miles per hour. The Mariana Trench experiences landslides regularly. Seismic monitoring has detected hundreds of small slides and several major collapses over the past 50 years. Each collapse reshapes the trench floor, burying whatever organisms lived in the impact zone. The ecosystem must repeatedly recover from catastrophic disruption. This creates a perpetually young community where succession never reaches a stable climax state. Rock composition varies along the trench walls. Some sections consist of volcanic basalt from the oceanic crust. Other areas expose serpentinite, a metamorphic rock formed when water reacts with mantle minerals. Serpentinite is weak and prone to landslides. Sections of trench wall made from serpentinite show extensive scarring from repeated collapses. Fluids seep from the trench walls at certain locations. These fluids are not superheated like hydrothermal vent emissions. They are cold, squeezed from the subducting plate by immense pressure. The fluids contain dissolved minerals and organic compounds. Bacterial communities colonize these seeps, forming patches of life on otherwise barren rock faces. Scientists discovered methane seeps on trench walls where gas bubbles rise from fractures in the rock. Methane-eating bacteria consume this gas, producing energy through chemosynthesis. The bacteria form mats that attract amphipods and other small organisms. These seeps create food webs disconnected from the rain of organic matter from above, demonstrating yet another way life finds energy in the deep ocean. The trench walls descend through multiple pressure zones. At 20,000 feet, the wall is in the upper Hadal zone. 30,000 feet, the same wall enters the lower Hadal zone where pressure increases another ton per square inch. Organisms living on the walls must cope with this pressure gradient. Species adapted to 20,000 feet cannot simply migrate down wall to 30,000 feet. The pressure difference is too extreme. Cameras dragged along trench walls have captured footage of fish swimming near vertical rock faces. What these fish were doing remains unclear. They might hunt organisms living in the wall. They might use the wall for navigation. Or they might simply explore their environment out of curiosity. The footage raises more questions than it answers about behavior in the deepest trenches. Sediment accumulates in pockets and ledges on the trench walls. These sediment deposits host burrowing organisms that excavate tunnels through the mud. The tunnels are visible in sonar images as networks of passages riddled through sediment layers. What creatures create these burrows and what they feed on remains unknown. Sampling sediment from vertical walls is technically difficult, limiting research. Some trench walls show evidence of past hydrothermal activity. Mineral deposits typical of vent systems have been found on rock samples collected from the walls. These inactive vents represent ecosystems that existed thousands or millions of years ago. When the vents shut down, their communities died or dispersed. The empty shells and tubes left behind fossilize, providing a record of past life in trenches. Earthquake activity is constant along trench walls. The subducting plate grinds beneath the overlying plate, building stress that releases in seismic events. Most quakes are small, barely detectable except by sensitive instruments. But major quakes occur periodically, triggering tsunamis at the ocean's edge far above. The 2011 Tohoku earthquake originated from a trench off Japan. The resulting tsunami killed over 18,000 people. The trench walls remind us that the deepest ocean is geologically active. These are not stable, ancient environments. They are young, dynamic, and dangerous. The creatures living here cope not only with extreme pressure and darkness, but also with catastrophic disturbances that can obliterate entire communities without warning. Yet life persists, and humanity's impact has reached even these isolated depths through unexpected channels. A plastic bag drifts through water at 29,000 feet depth in the Mariana Trench. The bag is faded and torn, but recognizable. It probably entered the ocean somewhere near a coastline, then drifted in currents for months or years before sinking to this depth. It represents proof that human pollution has contaminated even the most remote habitat on Earth. Scientists conducting deep trench research in 2018 discovered microplastic particles in amphipods collected from depths exceeding 33,000 feet. Analysis revealed these particles came from synthetic materials like polyethylene and polyester. The amphipods had ingested microplastics by feeding on organic matter containing plastic fragments, or by consuming smaller organisms that had eaten plastics. Plastics break down slowly in the deep ocean. Cold temperatures and lack of ultraviolet light prevent rapid degradation. A plastic bottle might persist for hundreds of years at Hadal depths before fully fragmenting into microplastic particles. Even then, the particles remain in the environment. They never truly disappear. They just become smaller and more widely distributed. The discovery shocked researchers. If plastic pollution has reached the deepest trenches, then no part of the ocean remains uncontaminated. The assumption that deep ocean isolation protected Hadal zones from human impact was wrong. Currents and settling materials create connections between the surface and the deepest depths. What we discard at the top eventually reaches the bottom. Microplastics found in Hadal amphipods raise questions about toxicity. Many plastics contain chemical additives like plasticizers and flame retardants. These chemicals leach out in seawater, potentially poisoning organisms that ingest plastic particles. Studies on shallow water animals show that microplastic ingestion causes gut blockages, reduced feeding, and transfer of toxic chemicals into body tissues. Similar effects probably occur in deep-sea organisms. But research on deep-sea plastic impact is limited. Collecting specimens from Hadal depths is expensive and difficult. Sample sizes are small. Most studies analyze only a few dozen individuals. This makes statistical conclusions uncertain. We know plastics are present in the deepest ocean. We do not know the full extent of their impact on deep-sea ecosystems. Plastics are not the only pollutants reaching Hadal depths. Industrial chemicals like polychlorinated biphenyls, known as PCBs, have been detected in trench sediments. These chemicals were banned decades ago, but persist in the environment. They accumulate in organic matter and eventually sink to the seafloor. Trenches act as final sinks for pollutants, concentrating chemicals in the deepest parts of the ocean. Heavy metals from mining operations and industrial discharge also reach trench depths. Mercury, cadmium, and lead have been measured in Hadal sediments at concentrations higher than surrounding abyssal plains. The trench topography funnels settling material, creating accumulation zones where pollutants concentrate. Organisms living in these zones face exposure levels exceeding anything their ancestors experienced throughout evolutionary history. Radioactive isotopes from atmospheric nuclear tests in the 1950s and 60s have been found in Hadal organisms. Carbon-14 levels in amphipod tissues exceed natural background levels, indicating they consumed organic matter contaminated with fallout. This provides unexpected dating information showing that organic material sinks from the surface to trench floor in a matter of decades, faster than previously thought. The speed of surface-to-depth transport has implications for carbon cycling. Trenches might sequester more atmospheric carbon than models predict. If organic matter reaches trench depths quickly and remains buried in sediment, it removes carbon from the active cycle for geological timescales. Understanding this process better could inform climate change models and carbon budget calculations. But the presence of pollutants in Hadal zones primarily demonstrates human reach. We have modified every environment on Earth, from the highest mountains to the deepest trenches. No ecosystem remains pristine. This realization changes conservation approaches. We cannot protect wilderness by declaring areas off-limits. The ocean is connected. What happens in one region affects all others. Cleanup of deep ocean plastics is impossible with current technology. The costs would be astronomical and the logistics insurmountable. We cannot remove millions of tons of plastic from the seafloor without destroying ecosystems in the process. The only solution is preventing additional plastics from entering the ocean at the source. Reducing plastic production, improving waste management, and developing biodegradable alternatives are the only practical approaches. The plastic bag drifting through the Hadal zone serves as a monument to human carelessness. It is visible evidence that our actions have consequences beyond what we can see. The deepest places on Earth bear our fingerprints, and the creatures living there now navigate an environment contaminated with materials that evolution never prepared them to encounter. Yet, among the pollution, some of the strangest life forms on Earth persist, including organisms that should not exist based on our understanding of cellular mechanics. A spherical shape rests on the trench floor, over 4 inches in diameter. It looks like a rock or a mineral concretion. But this object is alive. It is a xenophyophore, a single-celled organism of impossible size. Most cells visible to the naked eye measure fractions of an inch. This creature is large enough to hold in your hand, yet it consists of just one cell. The xenophyophore belongs to a group of protozoans, single-celled organisms that occupy an evolutionary position between bacteria and multicellular life. But unlike typical protozoans that are microscopic, xenophyophores grow to sizes that defy cellular biology. The largest specimen ever measured exceeded 8 inches in diameter. This violates principles that govern cell size limits. Normal cells cannot grow indefinitely because size limits their ability to transport nutrients and waste. Small cells have high surface area to volume ratios, allowing efficient exchange with the environment. As cells grow larger, volume increases faster than surface area. Eventually, the cell becomes too large to supply its interior with oxygen and nutrients. This is why most cells remain microscopic. Xenophyophores bypass this limitation through extreme adaptations. Their cell contents are not uniform. The organism consists of a network of branching tubes filled with cytoplasm. This increases internal surface area, allowing exchange between different parts of the cell. The structure resembles a sponge more than a typical cell. Nutrients and waste can diffuse through the tube network without needing to traverse the entire cell volume. The creature's test, its external shell, is constructed from sediment particles, tiny shells, and mineral fragments cemented together. The xenophyophore collects these materials from the surrounding seafloor and incorporates them into its test. This creates a protective housing and provides structural support that a cell membrane alone could not provide. Some xenophyophores secrete cement that binds the test materials together. Others rely on organic glues produced internally. Xenophyophores are abundant in the Hadal zone. Cameras have recorded densities exceeding 2,000 individuals per acre in some trench locations. They cover the seafloor like cobblestones, creating complex terrain that other organisms use for shelter and attachment sites. These xenophyophores themselves seem to be sessile, remaining in one location for their entire lives. What these giants eat remains partly mysterious. They extend pseudopods, temporary arm-like projections, from openings in their test. These pseudopods capture bacteria and organic particles from the surrounding water and sediment. The xenophyophore draws the food back into its cell body for digestion, but the energy budget seems insufficient. An organism this size should require more food than can be captured by passive filter feeding. Scientists discovered that many xenophyophores host bacterial symbionts inside their cytoplasm. These bacteria might provide additional nutrition through chemosynthesis, using chemicals from the sediment to produce organic compounds. The xenophyophore would then benefit from bacterial metabolism without needing to capture all its food from the environment. This would explain how such large organisms survive in the nutrient-poor Hadal zone. Reproduction in xenophyophores is bizarre even by protozoan standards. The organisms produce tiny flagellated cells that disperse in the water column. These reproductive cells might represent gametes that fuse with cells from other individuals, or they might be asexual propagules that settle and grow into new xenophyophores. No one has observed the complete life cycle, so the details remain unclear. The xenophyophores' nucleus, the cell structure containing genetic material, is not singular. The organism possesses thousands of nuclei scattered throughout its cytoplasm. This polynucleate condition allows the cell to grow extremely large without losing genetic control over distant parts of the cytoplasm. Each region of the cell has nearby nuclei to direct local protein synthesis and cellular activities. Different xenophyophore species have distinct test architectures. Some build simple spherical shells. Others construct elaborate tube systems or branching structures. The diversity of forms suggests different lifestyles and feeding strategies. Some species might specialize in capturing suspended particles. Others might feed primarily on bacteria in sediment. The morphological diversity reflects ecological diversity despite all species being single-celled. Xenophyophores are fragile. When collected for study, they often disintegrate during ascent to the surface. Pressure changes cause the test to crack and cytoplasm to leak out. Many specimens arrive at the surface as unidentifiable debris. This makes detailed study difficult. Most knowledge comes from photographs taken by seafloor cameras rather than laboratory analysis of intact specimens. Recent genetic studies revealed that xenophyophores are more closely related to certain amoebas than to other large protozoans. This suggests that gigantism evolved independently in xenophyophores rather than being inherited from a large ancestor. Natural selection favored increasing size in the Hadal environment, possibly because larger organisms have advantages in predator avoidance or competitive ability. The existence of single-celled organisms the size of bowling balls challenges our understanding of what cells can be. These creatures demonstrate that life finds solutions to problems we consider insurmountable, and they thrive in the deepest trenches, contributing to ecosystems we barely understand. As we descend the final miles toward the absolute bottom, pressure continues increasing toward levels that test the limits of biological possibility. We are approaching 35,000 feet depth. The pressure now exceeds 16,000 pounds per square inch. This is more than 1,000 times the atmospheric pressure at sea level. To grasp this force, imagine a single square inch of your body supporting the weight of 8 automobiles stacked vertically. Now, imagine that force applied to every square inch of your body simultaneously. At this pressure, water behaves differently than our experience would suggest. Density increases significantly. The water here is about 5% denser than water at the ocean's edge. This means objects that float at the surface might sink at this depth because their density relative to the surrounding water changes. Buoyancy calculations developed for surface applications fail in the Hadal zone. Sound propagates through this pressurized water at speeds exceeding 5,000 feet per second, nearly 10% faster than at the surface. This affects echolocation and makes acoustic communication more complex for any organisms using sound. The increased speed also changes how sound reflects and refracts, altering the acoustic environment in ways that would confuse surface-adapted animals. Chemical reactions occur at different rates under extreme pressure. Some reactions that proceed slowly at surface pressure accelerate at Hadal pressures. Others slow down or stop completely. This affects metabolism in organisms, requiring adaptations to maintain biochemical processes. Enzymes must be pressure adapted to function efficiently. Hadal organisms produce enzyme variants that work optimally at high pressure, but would fail at surface pressure. The phase diagram of water shifts under these conditions. Water can exist in liquid form at higher temperatures than normal, and ice can exist in forms that do not occur at surface pressure. These exotic ice forms remain theoretical in the ocean because water in trenches, while cold, is not cold enough to freeze even under pressure. But the possibility exists that under slightly different conditions, strange ice structures could form at the bottom of trenches. Gases behave unusually at this pressure. Carbon dioxide, normally a gas or dissolved in water, can form liquid puddles at pressures above 70 atmospheres. The Mariana Trench bottom experiences over 1,000 atmospheres of pressure. If carbon dioxide concentrations were high enough, liquid carbon dioxide pools could theoretically form on the seafloor. No such pools have been observed, but the conditions exist for their formation. The pressure crushes protective equipment designed for lesser depths. Glass that can withstand 20,000 feet implodes at 35,000 feet. Metal that holds at upper Hadal depths deforms at these pressures. Only specialized materials engineered specifically for the deepest trenches survive intact. Even then, safety margins are thin. A microscopic flaw in a pressure housing can trigger catastrophic failure. Organisms living at this depth have no gas spaces in their bodies whatsoever. Even traces of air would compress to dangerous densities or dissolve into body fluids under such extreme conditions. Fish lack swim bladders. Crustaceans have fluid-filled bodies rather than gas-filled spaces. Every structure is either solid tissue, liquid-filled, or flexible enough to compress harmlessly. Cell membranes must be reinforced to maintain integrity. Normal lipid membranes become too fluid under pressure, losing their barrier function. Hadal organisms incorporate special lipids with different molecular structures. These pressure-adapted lipids maintain proper membrane fluidity at depth. Without these modifications, cells would become leaky, allowing uncontrolled mixing of internal and external fluids. Proteins face denaturation pressure. The three-dimensional shape of proteins determines their function. Pressure distorts these shapes, potentially destroying enzyme activity and structural protein integrity. Hadal organisms produce pressure-stabilizing compounds like trimethylamine oxide that we encountered in the snailfish. These compounds counteract pressure effects on protein structure, allowing enzymes to maintain functionality. DNA itself experiences pressure effects. The double helix structure of DNA can be compressed and distorted by extreme pressure. Some organisms have DNA binding proteins that help maintain chromosomal structure under pressure. Others might have evolved DNA sequences less prone to pressure-induced distortion. The genetics of pressure adaptation are still being unraveled. Energy production faces challenges at these pressures. Mitochondria, the cellular structures that generate energy, must maintain membrane gradients while operating under crushing force. The efficiency of energy production decreases at extreme pressure unless adaptations compensate. Hadal organisms might produce less energy per food unit consumed than their shallow water relatives, necessitating slower metabolisms and reduced activity levels. The absolute deepest fish species observed was recorded at approximately 27,000 feet. Below that, depth. No fish have been found despite extensive searching. This suggests a hard limit for vertebrate life, possibly around 28,000 feet. The limit likely relates to protein stability or cellular mechanics that even maximum TMAO concentrations cannot overcome. But life continues below the fish limit. Invertebrates like amphipods and sea cucumbers persist to the very bottom of the deepest trenches. These creatures demonstrate that the pressure limit for fish is not a limit for all animal life. Different body plans face different constraints, and the absolute bottom awaits, where pressure peaks and where only a handful of humans have ever witnessed what exists in the deepest point on the entire planet. The seafloor continues dropping. We have descended past 35,000 feet. The walls of the Mariana Trench narrow slightly as we approach the deepest section, a crescent-shaped basin called the Challenger Deep. This is the absolute bottom, the lowest point in Earth's ocean. The pressure here approaches 16,000 pounds per square inch, over 1,000 atmospheres. In 1960, the bathyscaphe Trieste reached this depth with 2 men inside. The descent took nearly 5 hours. Jacques Picard and Don Walsh became the first humans to witness the deepest point on Earth. They spent only 20 minutes at the bottom due to concerns about the pressure vessel's integrity. The window had developed a crack during descent, raising fears of catastrophic failure. They dropped ballast and began emergency ascent before anything could go wrong. What Picard and Walsh saw astonished them. They reported seeing a flatfish swimming past their observation window. The scientific community initially dismissed this claim. Pressure at Challenger Deep should prevent fish from existing. But Picard insisted he saw what he saw. The identity of this fish remains controversial. Some scientists suggest it might have been a sea cucumber or other invertebrate misidentified in the poor lighting conditions. In 2012, filmmaker James Cameron piloted a submersible called Deep Sea Challenger to the bottom of Challenger Deep. His solo dive lasted several hours, allowing time for scientific observations and sample collection. Cameron described the seafloor as barren and desolate. The sediment appeared light-coloured, almost white, covered in a fine layer of organic ooze. Small amphipods scurried across the bottom, the only visible animals. Cameron's submersible experienced multiple equipment failures during the dive. Hydraulic fluid leaked from the manipulator arms, creating an oil slick that contaminated samples. Thrusters malfunctioned, limiting maneuverability. One entire system of scientific equipment failed completely under the pressure. The submersible barely completed its mission before critical systems would have failed entirely. This highlighted how even the most advanced technology struggles at these depths. Since Cameron's dive, only 2 other humans have reached Challenger Deep. In 2019, Victor Vescovo piloted the submersible limiting factor to the bottom. His dives were part of the 5 Deeps expedition, which visited the deepest point in each of the world's oceans. Vescovo made multiple trips to Challenger Deep, collecting samples and conducting surveys. He described seeing plastic bags and candy wrappers on the seafloor, providing heartbreaking evidence that human pollution has reached even here. Remotely operated vehicles have visited Challenger Deep more frequently than crewed submersibles. These robots can remain at depth longer and take greater risks without endangering human life. They have collected sediment cores, photographed organisms, and measured water chemistry. Each expedition reveals new species and unexpected biological discoveries. Pressure at the bottom of Challenger Deep forces special considerations for sample collection. Containers sealed at the bottom trap water at extreme pressure. As the container ascends, internal pressure remains high, while external pressure decreases. This pressure differential can shatter containers or blow seals. Engineers developed pressure-maintaining devices that keep samples at bottom pressure until they can be properly handled at the surface. Without these devices, many samples would be destroyed during ascent. Temperature at the bottom reads slightly above freezing, around 34 degrees Fahrenheit. This is warmer than expected. Geothermal heat leaking through the seafloor raises the temperature slightly above ambient deep water temperature. This hints at active geological processes occurring beneath the trench floor, possibly related to the subduction zone creating the trench. The seafloor sediment is softer than typical abyssal sediment. Cores extracted from Challenger Deep show fine clay particles mixed with organic material. The sediment is almost fluffy, easily disturbed by ocean currents. Landing a submersible creates clouds of suspended sediment that take hours to settle. Visibility drops to near zero during landing and takeoff operations. Scientists have calculated that if Mount Everest were placed in Challenger Deep, over a mile of water would cover its summit. The trench is so deep that light would never reach Everest's peak, even if it were positioned at the bottom. This depth is difficult to comprehend. It represents a vertical distance greater than the cruising altitude of most commercial aircraft. Challenger Deep is not completely flat. Multi-beam sonar mapping reveals small hills and depressions across the floor. These features rise or drop by dozens of feet, creating local topographic variation. Different species might occupy different microhabitats, separated by just these small elevation changes. The ecosystem could be more spatially complex than it appears from simple depth measurements. The descent to Challenger Deep represents the longest possible drop in the ocean. From the waves above to the bottom below spans nearly 7 miles. An object dropped from the surface would take over an hour to reach the bottom, accelerating until drag force balanced gravity in the dense, pressurized water. And at that bottom, life persists in forms we are only beginning to understand. We have reached the bottom. The depth gauge reads 35,876 feet, though exact measurements vary slightly, depending on survey methods. This is Challenger Deep, the deepest known point in Earth's ocean. We are standing in a crack in the planet's crust, a scar created by tectonic forces so powerful they bend solid rock. The pressure here is crushing beyond imagination. Every square inch experiences a force exceeding 16,000 pounds. Your body would be compressed to a fraction of its normal size if exposed to this pressure. Bones would crack. Organs would collapse. Death would be instantaneous, occurring faster than your nervous system could process pain signals. Yet the seafloor is not sterile. Sediment samples collected from the bottom contain bacteria living in the top layers of mud. These bacteria metabolize organic material that has drifted down from the surface miles above. They represent the base of a food chain operating at Earth's absolute pressure limit. How these bacteria maintain cellular function under such extreme force remains an active research question. Amphipods scurry across the sediment, disturbing the fine particles with their movements. They are smaller than the supergiant amphipods found at shallower Hadal depths, typically measuring under an inch long. But they are abundant, with densities estimated at hundreds per square yard in some areas. They feed on bacteria and organic detritus, processing the limited nutrients that reach this depth. Sea cucumbers crawl slowly across the bottom, ingesting sediment and extracting what little organic matter it contains. These creatures are the same basic body plan as sea cucumbers found worldwide, but modified for extreme pressure. They are translucent, allowing you to see internal organs through their body wall. Movement is incredibly slow, sometimes just inches per hour. Energy conservation is critical when food is this scarce. The sediment itself holds scientific importance. It contains a record of Earth's history stretching back millions of years. Each layer represents a different time period. Buried in the mud are microfossils, chemical signatures of past climate conditions, and evidence of ocean chemistry changes. The Challenger deep sediments are among the most pristine archives of Earth's past because they are undisturbed by currents or biological activity in the way shallower sediments are. Recent sediment cores revealed something disturbing. The top layer contains microplastic particles, synthetic fibers, and other human-made debris. The deepest point on Earth is contaminated with our waste. This discovery made international headlines, forcing recognition that no part of the ocean remains pristine. Our impact reaches everywhere. The water chemistry at Challenger Deep differs slightly from water at shallower depths. Dissolved oxygen levels are low, but not zero. Organisms here survive on minimal oxygen, extracting every available molecule. Carbon dioxide concentrations are elevated due to the accumulated respiration and decay occurring throughout the water column above. The water is slightly more acidic than surface seawater as a result. Salinity is higher than average seawater. The extreme pressure forces more salt into solution. Additionally, water seeping from the subducting tectonic plate carries dissolved minerals that increase salinity. This creates a dense brine layer hugging the bottom. The brine does not mix readily with water above it, forming a distinct layer that organisms must adapt to. Scientists have measured earthquake activity at Challenger Deep using seismometers placed on the seafloor. The data reveals constant micro-earthquakes as the Pacific Plate grinds beneath the Philippine Plate. Larger quakes occur periodically, shaking the entire trench. These quakes can trigger landslides on the trench walls and turbidity currents that sweep across the floor, redistributing sediment and potentially burying organisms alive. The future of Challenger Deep remains uncertain in geological terms. The trench is widening and deepening as subduction continues. In millions of years, it might become even deeper, setting new records for Earth's lowest point. Or shifting plate tectonics might close the trench, raising the seafloor and eliminating the deepest habitat. Geological time operates on scales that make human lifespans irrelevant. For now, Challenger Deep remains the ultimate destination for deep-sea explorers. It is the bottom, the end of descent, the deepest we could go. Standing here in a submersible, surrounded by darkness and pressure, you realize how alien our own planet can be. This is Earth, yet it feels like another world. And the creatures surviving here have adapted to conditions that challenge our understanding of life itself. The fish ahead represent the deepest observation ever recorded of vertebrate life. Cameras positioned at 26,900 feet in the Mariana Trench captured footage that redefines our understanding of fish adaptation limits. A snailfish, pale and translucent, swims past the camera. This is the deepest observation of a fish ever recorded by science. The pressure at this depth approaches 8 tons per square inch. No fish has been found deeper despite extensive searching. This depth likely represents the absolute limit for fish life. Below approximately 27,000 feet, the biochemical adaptations required to stabilize proteins and maintain cellular function reach their maximum effectiveness. Even with maximum concentrations of pressure-stabilizing compounds, proteins begin to fail. Cell membranes lose integrity. The fish body simply cannot maintain function. The snailfish at this depth appears ghostly. Its body is almost transparent, with minimal pigmentation. Coloration serves no purpose in total darkness, where visual predators do not exist. Evolution has stripped away pigment production, redirecting resources to more essential functions. The fish looks more like a jellyfish than a typical vertebrate. Its swimming style is slow and energy conserving. The fish drift more than swims, using minimal fin movements to maintain position. In an environment where every calorie matters, wasteful movement means death. The snailfish has perfected efficiency, moving only when necessary and resting whenever possible. The skull structure is incomplete, with gaps between bones. This allows slight compression without damage. A rigid skull would crack under pressure changes or impacts. The flexible skull distributes force and permits the brain to compress slightly when pressure increases without suffering trauma. It is an engineering solution that would never work in terrestrial environments, but functions perfectly here. Muscle tissue is gelatinous, softer than typical fish muscle. This gives the fish a flabby appearance but provides flexibility under pressure. The muscles contain high water content and minimal connective tissue. They generate less force than surface fish muscles, but require less energy to operate. This trade-off favors survival in the deep Hadal zone. The fish's eyes are small but functional. They detect bioluminescence from prey organisms. The retina contains high concentrations of light-sensitive pigments, maximizing detection of faint glows in total darkness. But the eyes cannot form sharp images. They provide light direction detection rather than visual acuity. This is sufficient for hunting in an environment where touch and chemical senses matter more than vision. Feeding behavior observed in the footage shows the snailfish approaching small amphipods. The fish opens its mouth and creates suction, drawing in prey along with water. The prey is swallowed whole, without chewing. Teeth are small and numerous, designed to grip rather than tear. Everything about the fish's anatomy prioritizes energy efficiency over power. Reproduction remains mysterious. No one has observed mating or found snailfish eggs at these depths. The fish likely gives birth to live young or deposits eggs in protected locations that cameras have not yet discovered. The young must be pressure adapted from birth, developing in the same extreme environment as adults. There is no shallow nursery habitat for these fish. The discovery of fish at 26,900 feet shocked scientists. Previous theories suggested fish could not survive below 25,000 feet. This fish extended the known limit by almost 2,000 feet. But subsequent searches at greater depths have found no fish. The limit appears genuine. Below, approximately 27,000 feet, fish anatomy and biochemistry reach their breaking point. Invertebrates continue to 36,000 feet because they have different body plans and metabolic systems. They lack complex organ systems that fish possess. Their simpler biology proves more adaptable to extreme pressure. This demonstrates that different lineages of life have different fundamental limits imposed by their evolutionary history. The snailfish at 26,900 feet represents an evolutionary endpoint. This species has pushed fish biology to its absolute limit. It exists at the boundary between possible and impossible. 1,000 feet deeper, and the physics and chemistry of life prohibit fish from existing. This fish swims at the edge of what vertebrate life can achieve on Earth. Studying these fish provides insights into pressure adaptation that might apply to other extreme environments. Understanding how proteins stabilize under pressure could inform research into preserving biological materials. The compounds that allow these fish to survive might have industrial applications in high-pressure processes. Nature has already solved problems that engineers struggle with. But the fish's existence also highlights fragility. These populations are small, isolated to the deepest trench sections. They cannot escape to shallower depth if conditions change. If deep ocean warming or pollution impacts their habitat, they have nowhere to go. They could disappear before we fully understand them. And beneath them, where fish cannot venture, other forms of life persist in the seafloor's ancient ooze.